There is a map of the universe we all hold in our minds. It is a place of breathtaking density, of furious light. We imagine a celestial tapestry, woven from the threads of a billion galaxies, each one a glittering jewel stitched into the black velvet of space. This mental portrait is one of fullness, of cosmic abundance. For millennia, we have looked up at the night sky and seen a canvas so crowded with stars, so rich with possibility, that the concept of true, absolute emptiness seemed like a contradiction. The universe, we felt, was fundamentally about times, something asterisk, not nothing. This intuition, this deeply held belief in a cosmos brimming with matter, has guided our exploration from the very beginning. But it is an illusion, a beautiful, comforting, and local deception. Recent discoveries have forced us to confront a startlingly different reality. Science has unveiled a new chart of existence, one that shows the familiar rivers of light are just shimmering coastlines, bordering an ocean of profound, almost incomprehensible darkness. And in that ocean, there are regions of such staggering vacancy they challenge our most basic understanding of cosmic structure. Astronomers have found a place where the lights have gone out. They have found a hole in the fabric of the cosmos. To understand the shock of this revelation, we must first journey back in time to an era when our cosmic map was not just incomplete, but entirely wrong. For most of human history, the universe was the sky above our heads. The stars were fixed points of light, perhaps lamps hung in a celestial dome or divine fires in the ether. The planets were wanderers, their strange loops a mystery that fueled astrology and religion. This was a small, intimate cosmos, with Earth at its very center. The revolution began slowly, with careful observation and courageous thought. Copernicus displaced our world, setting it in motion around the sun. Galileo, with his rudimentary telescope, revealed that the moon had mountains and that Jupiter was attended by its own orbiting moons. The universe was becoming larger, more complex. Yet, even as our solar system expanded in our perception, the grander structure remained a mystery. The faint, milky band across the sky, our own galaxy, was seen as the entirety. The countless stars we could discern were believed to be the universe's full population. The faint, nebulous smudges seen through early telescopes were mysteries. Were they clouds of gas within our own Milky Way, birthing new stars? Or were they something else entirely? The debate raged for decades, a foundational argument about the scale of existence. The breakthrough came in the 1920s, in the cold, thin air atop Mount Wilson in California. There, an astronomer named Edwin Hubble used the colossal Hooker telescope, the most powerful instrument of its time, to stare at one of these smudges, the Andromeda Nebula. He was searching for specific types of stars, known as Cepheid variables. These stars have a remarkable property. Their brightness pulses at a regular rate, and that rate is directly linked to their true, intrinsic luminosity. They are cosmic lighthouses, standard candles. By comparing how bright a Cepheid star appears from Earth with how bright we know it truly is, we can calculate its distance with precision. Night after painstaking night, Hubble exposed glass photographic plates, capturing the faint light from Andromeda, and then he found one, a pulsing Cepheid variable star. He did the calculations, checking and rechecking his figures. The result was unambiguous, and it shattered the known universe. Andromeda was not a gas cloud inside our galaxy. It was nearly 1 million light-years away, an entire galaxy in its own right, a colossal island of stars, gas, and dust, comparable in size to our own. In a single moment, the universe expanded by an unimaginable factor. Our galaxy was not the whole story. It was a single sentence in an infinite library. This discovery triggered a new, grand ambition to map this new, vaster cosmos. If there were other galaxies, how were they arranged? Were they scattered randomly like seeds thrown to the wind? Or was there some underlying pattern, some grand architecture to reality? The work began with astronomers painstakingly cataloguing galaxies, one by one. plotting their positions on the two-dimensional dome of the sky. But this was like trying to understand a forest by looking at its canopy from a plane. You could see the clusters of trees, but you had no sense of depth. The crucial third dimension, distance, was missing. Hubble's work with redshift provided the key. He observed that the light from distant galaxies was stretched, shifted toward the red end of the spectrum. He correctly interpreted this as evidence that the galaxies were moving away from us. Crucially, the farther away a galaxy was, the faster it was receding. The universe was expanding. This relationship between redshift and distance gave astronomers their cosmic yardstick. By measuring the redshift of a galaxy, they could determine its distance from Earth. The great cartographers of the cosmos could finally begin their work in earnest. Throughout the mid-20th century, surveys were launched, each one pushing deeper into space, charting the positions of thousands of galaxies. A preliminary picture began to emerge. Galaxies were not scattered randomly, they clumped together. Our Milky Way is part of a small gathering called the Local Group. The Local Group is on the outskirts of a much larger gathering, the Virgo cluster. These clusters, in turn, seem to be linked together in even grander structures called superclusters, forming long, tenuous chains and massive walls. A cosmic web of matter was beginning to reveal itself. But this new map also hinted at something unsettling. Between these great filaments and walls of galaxies, there appeared to be nothing, vast regions of apparent emptiness. These were initially dismissed as observational gaps, areas of the sky that simply hadn't been surveyed yet. The assumption was that if we just looked harder, we would find the missing galaxies. The universe, after all, was supposed to be roughly the same everywhere, a principle known as the cosmological principle. Large-scale voids were not just unexpected, they were theoretically problematic. This brings us to 1981, and a team of astronomers led by Robert Kirshner. They were conducting a new redshift survey at the Kitt Peak National Observatory. Their project was to measure the distances to galaxies in a specific patch of the northern sky in the direction of the constellation Boötes, the herdsman. The work was methodical, almost tedious. They would point the telescope at a faint galaxy, measure its light spectrum, calculate its redshift, and plot its position in three-dimensional space. Then, they would move to the next galaxy. As they gathered their data, a disturbing pattern began to take hold. They found galaxies, as expected. But then, as they looked deeper into space, into a region about 700 million light-years away, the galaxies simply stopped. At first, they assumed it was a statistical fluke, a small pocket of emptiness. They widened their survey area, pointing their instruments to adjacent patches of sky. Again, they found nothing. They pushed their observations deeper, expecting to find the far wall of this gap. Still nothing. A sense of profound disbelief settled over the team. Was their equipment malfunctioning? Was there an error in their calculations? They checked everything. The instruments were sound, the mathematics was correct, the data was unequivocal. They had stumbled upon a region of space of such monumental emptiness, it defied all contemporary models of the universe. It was a void. A chasm in the cosmos. It was not a small pocket. As they continued to map its boundaries, the true, terrifying scale of their discovery became apparent. This was not a gap, it was an abyss. They had found what is now known as the Boötes Void, sometimes called the Great Nothing. To say the Boötes Void is large is a failure of language. Words like vast or immense are rendered meaningless by its scale. We must turn to analogy to even begin to grasp its proportions. Imagine our own galaxy, the Milky Way. It is a sprawling metropolis of some 200 billion stars, stretching 100,000 light-years from end to end. In our analogy, let us shrink this entire galactic empire down to the size of a single, humble grain of sand. Now, imagine a colossal sports stadium, a place that can hold 100,000 people. If our galaxy is one grain of sand, this stadium, filled to the brim with sand, would represent a significant supercluster of galaxies. It would be a bustling, crowded, and luminous volume of the cosmos. The Bootes void, on this same scale, would not be another stadium. It would be a structure the size of the entire planet Earth, an Earth-sized sphere, almost completely devoid of a single grain of sand. It is a volume of space so large that if our galaxy were placed at its center, we would not have even known other galaxies existed until the 1960s. The light from our nearest galactic neighbor would have taken that long to reach us. Let's try another perspective, one of travel. Imagine we have constructed a vessel capable of traveling at the speed of light, the ultimate cosmic speed limit. At this velocity, you could circle the Earth 7.5 times in a single second. You could reach our moon in just over a second, and Mars in a few minutes. To cross our own Milky Way galaxy would take 100,000 years. A significant journey, spanning countless human generations. Now, let us point our light-speed vessel towards the Bootes void. We enter its ethereal boundary. The starscape around us begins to thin out. The great, glittering walls of galaxies recede behind us into a shimmering curtain. Ahead, there is only blackness, an unyielding, perfect dark. We continue for a year, 10 years, 100 years. Millennia tick by. Civilizations rise and fall back on Earth. Our vessel, traveling at the maximum speed the universe allows, is still deep within the suffocating emptiness. To cross the Bootes void from one side to the other would take our light-speed ship approximately 330 million years. 330 million years of seeing almost nothing. When our ship finally emerged on the other side, the continents on Earth would have shifted into an unrecognizable configuration. The age of dinosaurs would be a distant geological memory. The entire evolutionary history of humanity, from the first hominids to the present day, could have played out more than 100 times over during this single crossing. The discovery of this supervoid, and others like it, forced a radical rethinking of cosmic architecture. The universe was not a uniform sea of galaxies. It was something more complex, more structured, more empty. The model that has emerged is that of the cosmic web. Imagine a spider's web on a cool, misty morning, glistening with dew. The long, impossibly thin strands of silk are where the dewdrops collect. These are the filaments of the cosmos. These filaments are not made of silk, but of dark matter, the invisible gravitational scaffolding of the universe. And the dewdrops clinging to them are the galaxies and clusters of galaxies. Where the filaments intersect, you find massive nodes, the great superclusters teeming with thousands of galaxies, blazing with the light of trillions of stars. But the most striking feature of the spider's web is not the silk. It is the vast, empty spaces in between the strands. These are the cosmic voids. The Bootes void is simply one of the largest of these empty volumes we have yet discovered. Our universe is not a soup, but a foam, a network of bubbles. All the matter we can see, all the stars, all the galaxies, all of life, exists on the thin surfaces of these bubbles. Inside them is the vast, quiet, and lonely emptiness. But how could such a structure form? How could the universe, which began in a state of near-perfect uniformity, develop such extreme landscapes of feast and famine? The answer lies in the very first moments of creation. In the instant after the Big Bang, the universe was an incredibly hot, dense plasma. While it was remarkably uniform, it was not perfectly so. Quantum mechanics dictates that at the smallest scales, there are tiny, random fluctuations in energy and density, microscopic ripples in the fabric of space-time, popping in and out of existence. Ordinarily, these would average out and disappear. But in the first fraction of a second of its life, the universe underwent a period of hyperacceleration known as cosmic inflation. It expanded faster than the speed of light, stretching from smaller than an atom to larger than a grapefruit in an infinitesimal moment. This explosive growth took those minuscule quantum fluctuations and stretched them to astronomical proportions. Tiny density variations became the seeds of cosmic structure. After inflation ended, the universe was left with a primordial soup that had slightly denser regions and slightly less dense regions. And then, the most powerful force in the cosmos began its patient, relentless work: gravity. For billions of years, gravity has been playing a cosmic game of rich get richer. The regions that started out with slightly more matter had slightly stronger gravity. They began to pull in matter from their surroundings. As they pulled in more matter, their gravitational pull grew even stronger, allowing them to pull in yet more matter. Over eons, these overdense regions collapsed to form the first stars, then galaxies, and eventually the colossal superclusters that lie at the nodes of the cosmic web. Conversely, the regions that started out with slightly less matter had weaker gravity. They lost out in this cosmic competition. Any matter they did have was slowly but surely siphoned away by their more massive, gravitationally dominant neighbors. These underdense regions grew emptier and emptier, expanding to become the great cosmic voids. The Boötes void is the result of this process, writ large. It is an ancient realm that lost the gravitational war, a testament to the formative power of tiny initial imperfections. So what is it truly like inside this great nothing? Is it an absolute vacuum? A perfect negation of existence? The reality is subtly more complex, and perhaps even lonelier. The Boötes void is not perfectly empty. In the 1980s, astronomers began a meticulous hunt for any light within its dark confines. After years of searching, they found a handful of galaxies. To date, we have identified only about 60 galaxies within this enormous volume, a space that should, by all rights, contain thousands upon thousands. These galaxies are strange, solitary figures. They are often spiral-shaped, and they tend to form a peculiar tubular structure, as if they are the last vestiges of a filament that was almost entirely erased. Imagine a civilization evolving on a planet in one of these lonely galaxies. Their astronomers would look out into the night sky and see almost nothing. Their own galaxy would be a brilliant swirl of light overhead, but beyond it, there would be an unbroken, eternal blackness. No Andromeda to inspire questions about other island universes. No Virgo cluster to hint at a grander cosmic society. For such a civilization, the idea that they were utterly alone in the universe would not be a philosophical question, but an observational fact. Their cosmological models would be profoundly different, perhaps leading them to believe that their galaxy was the sole creation, a single miracle in an infinite, sterile void. The discovery of the cosmic web, from their vantage point, would be almost impossible. It is a chilling thought. Our understanding of the universe, our ability to even conceive of its true scale and structure, is a direct consequence of our privileged address in a crowded, luminous suburb of the cosmos. Furthermore, the void is only empty of what we call baryonic matter, the stuff of stars, planets, and people. But the cosmos, we now know, is dominated by two other mysterious components. The void is still filled with dark matter. This invisible substance, detectable only through its gravitational influence, is still present, though at a much lower density than in the filaments. It forms a diffuse, faint scaffolding that the visible galaxies have abandoned, and even more pervasively, the void is filled with dark energy. This is the mysterious force that is causing the expansion of the universe to accelerate. It is an intrinsic property of space itself, a kind of anti-gravity that pushes everything apart. In the dense superclusters, gravity is strong enough to overcome this push, holding galaxies together. But in the voids, where gravity is weak, dark energy reigns supreme. The emptiness of the voids is, in fact, helping to drive them to become even larger, pushing the walls of galaxies further and further apart. The voids are not passive, they are active agents in the disassembling of the cosmos. And the Boötes void is not unique. As our maps of the universe have become more complete, we have found many others. The local void sits right next to our own local group of galaxies. Our Milky Way is currently flying away from its edge at high speed. The Eridanus supervoid, also known as the CMB cold spot, is another colossal structure, so large and empty that it leaves a noticeable cold imprint on the cosmic microwave background radiation the afterglow of the Big Bang itself. Emptiness, it turns in, is not the exception in the universe. It is the rule. The filaments, the clusters, the galaxies, our world, we are the exception. Life exists on the thin, luminous froth of a cosmic ocean of darkness. This realization has profound implications for the ultimate fate of the universe. As dark energy continues to accelerate cosmic expansion, the voids will grow, the great filaments of the cosmic web will be stretched thinner and thinner until they snap. The superclusters of galaxies, which are currently moving apart from one another, will accelerate away at an ever-increasing pace. A time will come in the far distant future when the light from these receding superclusters will be stretched so much that it will become undetectable. They will pass over a cosmic horizon, disappearing from our view forever. The grand cosmic web will dissolve. What will be left are gravitationally bound superclusters, each one an isolated island universe in an endless, expanding void. Future astronomers within our own descendant supercluster, Laniakea, will look out and see only the galaxies bound within it. All other superclusters will have vanished from sight, their existence becoming the stuff of legend, of ancient, unverifiable texts. The universe will become a lonely archipelago of light. Eventually, even these islands will die. The stars within them will burn out. The remaining matter will be consumed by black holes. And those black holes themselves will eventually evaporate over unimaginable timescales through Hawking radiation. The final state of the universe, as dictated by our current understanding, will be a cold, dark, and ever-expanding void, populated only by a sparse mist of fundamental particles. The universe, it seems, began in fire, but will end in emptiness. The Boötes void is not just a feature of our current universe, it is a preview of its ultimate destiny. The discovery of the Great Nothing was a moment of profound cosmic reorientation. It was as significant as Copernicus moving the Earth from the center of the solar system, or as Hubble revealing the existence of other galaxies. It has taught us that the universe is defined as much by its absences as by its presences. It has shown us that our home is a place of rare and precious density, a fortunate concentration of matter that allowed for the formation of stars, planets, and life. We live in an oasis, but the desert is far, far larger than we ever imagined. The map of the universe is still being drawn. With every new telescope, every new survey, we fill in more of the details. We trace the filaments with greater precision, we identify the clusters, and we plumb the depths of the voids. And with each new discovery, we find a cosmos that is stranger, more extreme, and more magnificent than our theories had predicted. We are cartographers of the infinite, driven by a relentless curiosity to understand our place within this grand and terrifyingly empty design. The Boötes void is a silent, dark testament to the true scale of our reality. It reminds us that in a universe dominated by nothing, the something we call home is all the more miraculous. The search to understand it, to map its boundaries and uncover its secrets, continues. Because in confronting the great emptiness, we learn the most about the preciousness of our own improbable existence. The universe is full of astonishing beauty. Stars burn brightly for billions of years, shaping the cosmos around them. But just as all things have a beginning, they also have an end. Every star and every galaxy, no matter how grand, will eventually fade. Their light will be extinguished as they reach the end of their life cycle. These cosmic graveyards are scattered across the universe. They are silent witnesses to the passing of time. They witness the inevitable decline of stars that once lit the night sky. Can life survive in a universe slowly running out of energy? And what does this mean for the future of everything we know? Join us on a journey through the galactic graveyards. The last remnants of the cosmos whisper stories of the universe's final chapters, the birth of a star from nebula to nuclear furnace. Stars are born in the cold, vast, and beautiful reaches of interstellar space. Immense clouds of gas and dust swirl in the silent darkness. These clouds, known as nebulae, can stretch across hundreds of light years. They are vast ethereal structures painted with faint light from distant, older stars. Despite their tranquil appearance, these clouds hold potential for incredible transformation. The birth of a star begins when a part of this cloud collapses under its own gravity. This may be nudged by a shock wave from a nearby supernova. It could also be from the gravitational pull of a passing star. Countless trillions of gas and dust particles are drawn closer together. As this happens, they begin to heat up. Their random motions are converted into thermal energy. The material compresses more and more as time goes on. Initially, the gases can cool and radiate this heat away, but gravity relentlessly pulls the particles closer. The material begins to pack together. It becomes so dense that heat can no longer easily escape. The temperature begins to rise dramatically. This is a process known as gravitational contraction. When enough mass accumulates, a tipping point is reached. The pressure at the center of the cloud becomes incredibly intense. The temperature rises to millions of degrees Celsius. The central core becomes a hot, dense, and glowing protostar. This is the earliest embryonic stage of a star's life. It is not yet a fully formed star, but it is a brilliant precursor to the energetic nuclear furnace that will emerge. During this protostellar stage, the object radiates tremendous energy. This comes from continued gravitational contraction, not nuclear fusion. The surrounding swirling cloud of gas and dust begins to flatten. It is pulled by the protostar's gravity and its own angular momentum. This forms a rotating protoplanetary disk. The disk is made of leftover material that did not collapse into the protostar. Over millions of years, this material can begin to clump together. It accumulates through accretion to form planets, moons, and asteroids. It can form all the other bodies that will make up a new solar system. The protostar continues to heat up as more matter rains down upon it. It then reaches a crucial final turning point. The temperature and pressure at its core rise to an extreme level. This level is around 15 million degrees Celsius. At this point, nuclear fusion begins to take place. Hydrogen atoms are forced together with such violence that they fuse. They fuse to form helium, releasing an enormous amount of energy in the process. This marks the true birth of the star. The fusion process generates the immense energy needed to sustain the star. This energy pushes outward against the crushing force of gravity. The star becomes a fully fledged, self-sustaining nuclear furnace. It is capable of producing vast amounts of energy. This energy will continue to fuel it for billions or even trillions of years. For a star to reach this stable stage, a balance must be met. The outward pressure from fusion must balance the inward pull of its own gravity. This delicate cosmic balancing act is known as hydrostatic equilibrium. If this balance is ever disrupted, the star will undergo dramatic changes. These changes are often catastrophic, but as long as it is maintained, the star will shine brightly. It will be a stable and predictable beacon, radiating energy into space. As the fusion process continues, the star's core becomes more stable. The outer layers of the star radiate the core's heat and light outward. These vast layers of gas and plasma are in constant turbulent motion. They give the star its characteristic brilliant glow. Over time, the energy from nuclear fusion continues to fuel the star. It remains in this stable, predictable state. It continues to burn hydrogen in its core for potentially billions of years. Stars are not all born in the same way. Their final, ultimate form depends almost entirely on their initial mass. A relatively small star like our own Sun will spend most of its life in this stable phase. It will calmly burn hydrogen in its core, but but a much larger star will burn through its fuel much more quickly. This could be 10 or 100 times the mass of the Sun. Its life is a brief and violent spectacle. It reaches the final stages of its life cycle far more rapidly. These massive stars will end their lives in dramatic, cataclysmic ways. They will end either as brilliant supernovae or by collapsing into a black hole. Smaller stars like our Sun will gently shed their outer layers. They leave behind a fading, cooling remnant known as a white dwarf. As the protostar forms, it can have a profound effect on the surrounding nebula. Strong, powerful winds of particles are driven by the protostar's intense radiation. These winds begin to blow away any remaining material. This clears material not yet condensed into the star or planetary disk. This radiation pressure pushes away the outer layers of the surrounding nebula. This clearing process is sometimes called photoevaporation. It helps to clear the space around the newly born star. This allows it to shine more brightly and spread its energy into the cosmos. Once the star reaches the stable stage of burning hydrogen, it enters the main sequence. This is the longest and most stable stage in the life cycle for most stars. For stars like our Sun, this stage lasts for billions of years. During this vast expanse of time, the star remains in perfect hydrostatic equilibrium. It maintains the delicate balance between outward pressure and inward gravity. During this long, peaceful phase, stars shine their brightest. Their life-giving light and heat radiate across space. This affects everything in their vicinity, including the potential for life on orbiting planets. In the case of our own Sun, it has been a stable main sequence star. This has lasted for about 4.5 billion years. It still has around 5 billion years of fuel left in this stage. As the Sun ages, it will eventually run out of hydrogen fuel in its core. The process of fusion will be forced to shift to heavier elements. The core will contract under gravity, becoming hotter and denser. The outer layers will expand dramatically, transforming the Sun into a red giant. This swollen, luminous star will engulf the inner planets. This will mark the beginning of the end of its life. It will shed its outer layers into space. It will leave behind a dense, hot core known as a white dwarf. For much more massive stars, the process is far more dramatic and violent. These stellar behemoths burn through their fuel much more quickly. They reach the end of their brief main sequence phase. They undergo a series of complex and increasingly rapid nuclear reactions. They burn heavier and heavier elements in their cores. This continues until they can no longer sustain the fusion process. The result is a supernova, a massive cataclysmic explosion. It releases an almost unimaginable amount of energy, briefly outshining entire galaxies. Stellar lifespans. How mass determines fate. The life of a star is a tale shaped primarily by its initial mass. This shaping occurs from its fiery birth to its quiet or violent death. The size of a star determines not only how long it will live, it also determines the dramatic and often spectacular way it will die. The entire process of stellar evolution is tied to the star's mass, from its birth in a cold nebula to its final dark end. Specifically, it is a story of how much material it contains. While all stars share certain fundamental life stages, their fates can vary. They vary from a slow, gentle fading to a cataclysmic explosion. Mass is the key player in determining how fast a star burns its nuclear fuel. The more massive a star, the higher the pressure and temperature in its core. This means its nuclear fusion reactions happen at a much faster rate. This increased rate of fusion allows the star to shine with a brilliant light. But it also means the star consumes its hydrogen fuel at an accelerated pace. Stars like our Sun are considered to be medium-sized. They have a lifespan of about 10 billion years. They burn their hydrogen more slowly and efficiently. This means they can maintain a stable, predictable state for a much longer time. In a stark comparison, a massive star might live for only a few tens of millions of years. This star might have 10 times the mass of the Sun. That is just a tiny fraction of the lifespan of a star like our Sun. The intense gravity inside these massive stars forces hydrogen atoms to fuse rapidly. This creates more energy, but it also means the star burns through its entire fuel supply much more quickly. As the star approaches the end of its hydrogen-burning phase, the balance shifts. The balance between the inward pull of gravity and outward pressure from fusion shifts. This is because the star's core has consumed much of its hydrogen. Without this primary fuel, the fusion reactions begin to slow down. In a smaller star like the Sun, this causes the core to contract and heat up. The outer layers of the star expand and cool, becoming a red giant. But in larger, more massive stars, the process is far more dramatic. As the core contracts, the temperature and pressure rise high enough. The star begins fusing heavier elements such as helium. Helium then fuses into carbon and then oxygen. In these massive stars, the fusion process moves rapidly through different elements. This creates a layered onion-like structure in the star's core. Each shell burns a different, heavier element in the star's final years. When a star is large enough, fusion can reach the point where iron is created. However, this marks the end of the line for the star. Iron cannot be fused into heavier elements to release energy. Unlike hydrogen, helium, and other lighter elements, fusing iron consumes energy. It consumes more energy than it produces. This is the crucial final moment that determines the violent death of the star. In a massive star, the core is now made of inert iron. It continues to collapse under its own immense gravity. This leads to a catastrophic runaway implosion followed by a titanic explosion. The shock wave from this explosion, a supernova, can outshine an entire galaxy. It releases an enormous amount of energy. It scatters the heavier elements forged in the star's core throughout space. These elements, such as gold, uranium, and platinum, are building blocks. They are the very building blocks for everything we see on Earth. Our planets, our oceans, and even we ourselves are made of these ashes. The explosion of a supernova may leave behind a dense, exotic remnant. This remnant at the core is either a neutron star or a black hole. A neutron star is a stellar corpse so incredibly dense, a single teaspoon of its material would weigh several billion tons. In the case of the most massive stars, the core's collapse is intense. It is so complete that it forms a black hole. This is a region of space where gravity is so strong that not even light can escape. On the other end of the mass spectrum, smaller stars follow a different path. These less massive stars follow a far more gentle path. Stars not massive enough to end in supernovae have a more gradual death. A star like our Sun has a mass of around 1 solar mass. It will eventually run out of the hydrogen fuel in its core. As hydrogen fusion slows, the core will contract. The outer layers of the star will expand dramatically. These stars become red giants, shedding their outer layers in a gentle wind. This forms what is known as a planetary nebula. It is a beautiful glowing cloud of gas and dust. What remains at the center is the hot, dense core of the star. This core has now turned into a white dwarf. A white dwarf is the dense, hot remnant of a star. It can no longer sustain any form of nuclear fusion. Without outward pressure from fusion, the white dwarf is compressed by its own weight. It is supported against a total collapse by electron degeneracy pressure. This quantum mechanical effect prevents it from collapsing any further. Over time, the white dwarf will simply cool and fade away. It becomes a cold, dark, and invisible remnant of its former self. The cooling process takes billions and even trillions of years. A white dwarf no longer shines as brightly as a living star, but it carries with it the memory of the star it once was. A small star undergoes a relatively calm and peaceful transformation. It sheds its layers slowly, and leaves behind a quiet, fading white dwarf. But stars with significantly more mass burn out quickly and violently. They leave behind remnants that can be some of the most extreme objects. These are some of the most exotic objects in the entire universe. The remnants of these massive stars are some of the densest objects we know. They are also some of the most mysterious, challenging our understanding of physics. Massive stars live very short lives compared to their smaller counterparts, but they play an absolutely essential role in the universe's evolution. During their brief, brilliant existence, they enrich interstellar space. They enrich it with the heavy elements created in their cores. These elements are crucial for the formation of rocky planets and moons. Ultimately, they are crucial for the emergence of life. Without the explosive death of these massive stars, life's building blocks would not exist. The chemical building blocks would not be as widely distributed across the cosmos. In this sense, massive stars contribute to the ongoing creation of the universe. Despite their short and violent lives, they provide raw materials for future generations. They provide materials for future generations of stars and worlds. The quiet demise and the explosive end. Massive stars can fuse heavier and heavier elements like carbon and oxygen. They fuse until they reach the point of no return at iron. Low-mass stars cannot do this. They do not have enough pressure and temperature in their cores. They cannot ignite the fusion of elements beyond helium. Without this ability, the star's fusion process comes to a final end. The result is the white dwarf, which is composed of fused material. This material, like carbon and oxygen, cannot undergo further nuclear reactions. White dwarfs are incredibly dense objects. They are typically only about the size of the Earth, but they can have a mass that is comparable to that of our Sun. This means a white dwarf is incredibly compact. All of its matter is squeezed into a very small hot volume. For instance, a single teaspoon of white dwarf material would weigh about 5 tons. This extreme density results from the collapse of the star's core. The core has now condensed into a very small, stable volume. The transition to a white dwarf does not happen immediately. It does not happen after the star becomes a red giant. Instead, this is a slow, gradual process that unfolds over billions of years. As the star loses its outer layers, it forms a planetary nebula. This beautiful expanding nebula gradually exposes its hot, dense core. During this time, the core remains very hot. It continues to radiate a tremendous amount of energy into space. However, there is no longer any fusion happening in the core. The white dwarf cannot sustain its brightness for a very long time. Over billions and trillions of years, it slowly cools and fades. Its once intense white-hot light dims as it radiates heat into space. Other stellar remnants like neutron stars or black holes can be active. White dwarfs, however, are relatively quiet, passive objects. They no longer produce any new energy through fusion. They do not exhibit the extremely strong magnetic fields of their cousins. They also do not have the extreme gravity of their more massive cousins. Instead, they simply cool down over time. They gradually lose their heat and become more difficult to observe. Eventually, after trillions of years, a white dwarf will have cooled down. It will no longer emit any detectable light. It will become a cold, dark, and invisible object known as a black dwarf. However, this cooling process is so incredibly slow. No black dwarfs are expected to exist in the current age of the universe. The universe itself is not yet old enough for a white dwarf to cool completely. The death of a low-mass star is a gradual fading of light. It is a slow and peaceful process, marked by the loss of its mass. It ends with the inevitable cooling of its stellar remnant, but this gentle process still has a significant impact on its environment. The beautiful planetary nebula enriches the surrounding interstellar space. It enriches space with heavier elements created in the star's core. These elements include carbon, nitrogen, and oxygen. In this way, the quiet death of a star gives rise to building blocks. These are the building blocks of new planets and new life in the universe. Moreover, white dwarfs are not just the final end of a star's journey. They also play an important role in the evolution of the galaxy. As these white dwarfs cool and fade, they can still interact with other stars. In binary star systems, a white dwarf may interact with a companion star. It may slowly accrete or pull material from it. If enough new material accumulates on the white dwarf's surface, a nova can occur. A nova is a sudden bright explosion. It is caused by the sudden ignition of the accumulated material. This explosion can briefly reignite the white dwarf. It causes it to shine with a brilliant renewed light before it cools again. A star's death and its transformation into a white dwarf may seem uneventful. It may seem uneventful compared to the spectacular end of massive stars, but it plays an essential role in the life cycle of stars and the universe. The material ejected during the red giant phase becomes part of interstellar medium. There it can eventually be incorporated into new stars and planets. It could even be incorporated into new forms of life. In this way, the quiet demise of low-mass stars is just another chapter. It is another chapter in the ongoing cyclical story of cosmic evolution. The death of a high-mass star is one of the most dramatic events in the universe. The star's core is composed primarily of iron. It can no longer generate the outward pressure needed to counteract gravity. The core begins to collapse rapidly. This process happens extremely quickly in a matter of mere seconds. During a supernova, the core's collapse creates a powerful shock wave. This sends the outer layers rushing outward at incredible speeds. The explosion releases a truly staggering amount of energy. This is equivalent to the total energy the star produced over its entire life. All of this energy is released in just a fraction of a second. The outer layers of the star are violently ejected into space. The core itself becomes either a neutron star or a black hole. Neutron stars have a mass between 1.4 and 2 times that of our Sun. But all of that mass is squeezed into a sphere with a radius of only 10 kilometers. The collapse of the core is so incredibly intense. It forces protons and electrons to combine, forming neutrons. This results in a star composed almost entirely of neutrons. It is held together by the immense crushing force of gravity. In addition to their incredible density, neutron stars have strong magnetic fields. They can also rotate at an incredibly rapid rate. When a star collapses into a neutron star, it conserves its angular momentum. This is the same principle that makes a figure skater spin faster. They spin faster as they pull in their arms. As a result, neutron stars can spin up to several hundred times per second. This rapid rotation creates extremely strong magnetic fields around the star. The magnetic field is so intense it can accelerate particles to near light speed. This creates powerful beams of radiation emitted from the star's magnetic poles. These beams of radiation are not constant. They sweep across space as the neutron star spins like a lighthouse beam. If these powerful beams happen to point toward the Earth, we can observe them. We observe them as regular repeating pulses of radiation. This phenomenon is what is known as a pulsar. Pulsars emit radiation across a wide range of wavelengths. This includes radio waves, X-rays, and even gamma rays. The incredible regularity and precision of these pulses make pulsars valuable tools. Astronomers use the timing of these pulses to study the neutron star's rotation. They also study its powerful magnetic field and the material around it. For the most massive stars, however, the collapse of the core is even more final. If the core's mass is large enough, gravity becomes incredibly intense. It can overcome the immense pressure from the neutrons, leading to a further collapse. This collapse continues until the core becomes a black hole. It becomes a singularity, a point with infinite density where our laws of physics break down. The boundary around a black hole is called the event horizon. Once any object or even light crosses this threshold, it can never escape. The size of this event horizon depends on the black hole's mass. A black hole with the same mass as our Sun would have a small event horizon. It would be only about 3 kilometers across, but if a much more massive star were to collapse, the black hole would be larger. It could be dozens of kilometers wide. Supermassive giants lurk at the centers of most galaxies. In their case, the event horizon can be millions of kilometers wide. These supermassive black holes can anchor the galaxies themselves. They influence the orbits of billions of stars, but even the smallest stellar mass black holes are truly remarkable. Within that small dark space lies more mass than an entire star. It is all compressed by gravity's final crushing hand. The formation of a black hole is one of the most mysterious processes in the universe. Once a black hole forms, it continues to pull in any matter that comes too close. It grows in size and in mass over time. While black holes themselves are completely invisible, their presence can be inferred. We can infer it by the powerful way they interact with nearby objects. For example, a black hole might pull matter from a companion star. This material forms a hot, glowing accretion disk around the black hole. As the material in this disk spirals inward, it heats up to high temperatures. It emits powerful radiation that can be detected by our telescopes. This process is one of the primary ways that we can observe black holes. This is true even though we can never see the black hole itself. The supernova explosion is a spectacular and violent end to a high-mass star, but it also has a lasting and profound effect on the surrounding universe. The immense energy released in the explosion creates elements heavier than iron. These elements are then scattered far out into space, enriching the interstellar medium. Without these supernovae, the universe would miss many important elements. These are the elements that make up the planets and life forms we know today. Supernovae act as the cosmic forges. They create the elements that are essential for the formation of planets. They create everything else in the universe. Moreover, the powerful shock waves from a supernova can trigger star formation. The intense energy and pressure can compress nearby gas clouds. This causes them to collapse and to form new stars. This is how the universe continuously evolves. The death of one generation of stars paves the way for the birth of the next. Supernovae are therefore not just the end of a star's life. They are also a necessary and vital step in the ongoing cycle of star formation, galactic evolution, how galaxies live, die, and merge. Galaxies, just like the stars they contain, are not eternal. They are vast, dynamic systems of stars, gas, dust, and dark matter. They are all bound together by the relentless pull of gravity, and they too go through their own life cycles and cosmic dramas. When we look at the galaxies scattered across the universe, we see more than stars. We see cosmic structures that grow, evolve, collide, and eventually fade. Their story stretches over billions of years, shaping the cosmos itself. The birth of galaxies began not long after the universe itself came into existence. In the aftermath of the Big Bang, matter was spread out nearly uniformly, but there were tiny ripples, tiny clumps of matter that began to pull together. These small initial overdensities slowly gathered more material. They created regions where gas could condense and the very first stars could form. Over time, the first galaxies were born. These early proto-galaxies were small and irregular in their shape. They were full of young, massive stars that burned incredibly hot and bright. They were far different from the large, structured galaxies that we see today, but they were the seeds of what would eventually come. As galaxies aged, they changed in both their form and their behavior. The gas clouds inside them collapsed to form new generations of stars. As those stars lived and died, they recycled material back into the galaxy. The death of massive stars in supernova explosions enriched the galaxies. They were enriched with heavy elements, seeding the formation of planets and moons. The cycle of star birth and death drove the evolution of galaxies for billions of years. It shaped their chemistry and their appearance. A young galaxy was a place of intense chaotic activity. It had a rapid rate of star formation and chaotic swirling motions. Over time, many galaxies settled into more stable, ordered structures. These became the grand, beautiful spiral galaxies we can observe today. Not all galaxies took the same path, however. Some grew large and ordered like our own Milky Way. They have vast, sweeping spiral arms stretching from a central bulge. Others became elliptical, massive but lacking delicate spiral pattern. Elliptical galaxies are often older and filled with aging, redder stars. They have relatively little star-forming gas left. Irregular galaxies, by contrast, resisted any neat classification. They were often shaped by violent collisions with their galactic neighbors. The universe is full of these varied and beautiful forms. Each one represents a different stage in a galactic life. Collisions and mergers play a central, often violent role in how galaxies evolve. The stars within galaxies are incredibly far apart. Direct collisions between them are exceptionally rare. The galaxies themselves, however, can and very often do collide. The force of gravity pulls them together across vast cosmic distances. When they finally meet, the results are truly spectacular. Their stars, gas, and dark matter all swirl and mix, reshaping their structures. In some cases, two spiral galaxies may merge to form a single giant elliptical galaxy. They lose their delicate, intricate patterns in the process of the collision. In other cases, collisions can trigger massive bursts of star formation. The gas clouds are violently compressed and collapse into new stars. These cosmic dances are not sudden events. Instead, they unfold over hundreds of millions of years. They slowly and inexorably alter the very face of the universe itself. Our own Milky Way galaxy is a part of this grand, ongoing process. It has grown to its current size through countless mergers with smaller galaxies. It has swallowed them up into its structure. The evidence of these past collisions can still be found today. We see long, faint streams of stars that stretch across our night sky. These are the ghostly remains of galaxies torn apart and absorbed by our own. In the distant future, our galaxy will face an even greater merger. The Andromeda Galaxy, our nearest large neighbor, is on a collision course. It is on a collision course with the Milky Way. In about 4 billion years, the two galaxies will begin to merge. They will create a new, much larger galaxy. The stars within the two galaxies will mostly avoid direct collisions, but the galaxies themselves will become one. Their beautiful spiral shapes will be destroyed and then rebuilt in the process. The life of a galaxy is also deeply tied to the amount of fuel that it carries. Stars form from cold gas, and without this gas, new stars cannot be born. Over time, galaxies can use up or lose much of their gas. They may form it into new stars, or powerful outflows driven by supernovae or black holes can blow it out. When the supply of this star-forming gas finally runs out, the galaxy grows quiet. It no longer produces very many new stars. Its population of stars grows older and redder. These galaxies are sometimes called red and dead. This is a sign that their days of active growth are now behind them. Supermassive black holes at the centers of galaxies add another layer to their story. This layer is often violent. Nearly every large galaxy, including our own, appears to have one. These black holes are millions or billions of times the mass of our Sun. They can have a profound influence on their entire host galaxies. This is especially true when they are actively feeding on the gas around them. As matter falls into the black hole, it releases a tremendous amount of energy. This sometimes ignites a quasar, a blazing beacon of light. A quasar can outshine the rest of the galaxy combined. These brilliant, energetic objects can be seen across billions of light years. They are powerful reminders of the violent mergers that often power them. Even the smaller dwarf galaxies are not spared in this cosmic drama. These dwarf galaxies often fall into the gravitational grip of larger ones. Their stars and their gas can be stripped away in long, beautiful tidal streams. Some of them are absorbed entirely. They leave behind only the faintest ghostly traces of their former existence. This process continues on endlessly. Smaller galaxies feed the larger ones. The larger ones combine to form the true giants of the cosmos. The universe is in a sense built on these mergers. Each new collision adds to the vast cosmic structures that we see today. The scale of these events is difficult to truly comprehend. A single merger can take billions of years from beginning to end. The first encounter may pull the galaxies into elongated, distorted shapes. It can send great sweeping arcs of stars out into the surrounding space. Then, after looping around one another, the galaxies may pass apart. They are only to be drawn back together again by the relentless pull of gravity. With each new pass, they lose energy. They finally combine into one single massive galaxy. For the stars inside, this long process means a rewriting of their orbits. A star may have once circled calmly around the center of a spiral disk. It may find itself flung far out into the outer halo of the new galaxy, or it could be sent on a chaotic plunging orbit through a dense galactic core. The very structure of the cosmic web is shaped by these interactions. Its vast clusters and superclusters of galaxies are shaped by gravity. Without these mergers, galaxies might have remained much smaller and less diverse. The rich variety of forms we see in the universe today owes something to gravity. The beautiful spirals, massive ellipticals, and chaotic irregulars are all shaped by it. Gravity is constantly, relentlessly drawing the galaxies together. Astronomers study these mergers to understand the past and predict the future. Powerful computer simulations allow us to watch the slow process of galaxies combining. We can watch this process in an accelerated form. These simulations can reveal the fine, intricate details of the process. They show how stars and gas are redistributed and how tidal tails are formed. They also show how central black holes grow to become supermassive giants. Observations with our powerful telescopes give us real-life snapshots. Telescopes like Hubble and James Webb show mergers at all different stages. This ranges from the very first contact to the final complete coalescence. By piecing all of these together, we can reconstruct a galactic evolution. We can reconstruct the long and often violent story. In the grand timeline of the universe, mergers are the true milestones. They mark the moments of a profound transformation. This is when the old galaxies give way to the new ones. Even on scales so vast, they seem eternal. Nothing is static. Everything changes. And in that long process, the seeds of new stars and worlds are sown. This ensures that even in the midst of violence, creation continues. The Fermi paradox, searching for life in a graveyard of stars. The silence of the universe is one of its greatest and most profound mysteries. When people look up at the night sky, they imagine other beings. Somewhere among the countless stars, others must be staring back at their own skies. They must be wondering the same thing. The sheer numbers of the cosmos almost seem to demand it. The Milky Way galaxy alone holds hundreds of billions of stars. Many of them have their own planets. Beyond that, there are trillions of other galaxies in the observable universe. Even if a tiny fraction of these worlds could support life, the odds are high. The odds seem overwhelming that intelligent life must exist somewhere else. Yet when we listen and when we search, we hear nothing. This is the very essence of what is called the Fermi paradox. It is not simply the question of whether life exists. It is why the universe seems so empty when it should be alive with voices. The paradox is named after the physicist Enrico Fermi. During a casual conversation in the 1950s, he asked a simple question. His haunting question was, where is everybody? His point was that if the universe is so incredibly vast, civilizations could rise. They have had billions of years to rise and to expand. It should only take a small portion of that time for one to spread across the galaxy. Even moving slowly over millions of years, a civilization could travel. It could travel from star to star, building colonies. It could leave behind unmistakable evidence of its presence. The fact that we see none of this suggests something is missing. Either intelligent life is far rarer than we think, or it does not last long. It does not last for very long once it finally appears. The more that astronomers learn about planets, the more pressing this question becomes. When telescopes first began to detect exoplanets, no one knew how common they were. This was in the 1990s. Now we know that planets are everywhere. Many stars have entire systems of their own. Some of them have rocky Earth-like worlds in the right zone for liquid water. If the Earth is not unique, and if nature repeats itself, life's ingredients exist. The very ingredients for life should be scattered throughout the entire galaxy. Life on Earth appeared very quickly. It appeared almost as soon as the conditions allowed it to. That suggests that it may not be a very difficult step for life to begin. And yet when it comes to advanced civilizations, the silence remains absolute. Some scientists think the problem lies with the way that we are looking. Our search for alien life often focuses on radio signals. This is because radio waves can travel for vast distances across space. They can still be detected. For decades, projects like SETI have been scanning the skies. SETI is the search for extraterrestrial intelligence. They have been listening for any sign of a technological source. A deliberate broadcast, or even a faint leak from another world, would be proof. It would reveal that we are not alone. But so far, the radio sky has remained completely quiet. There have been a few occasional blips and some strange signals, but none of them have ever stood up to a repeated study. The silence may not mean that nobody is out there. It may mean they are not using the kind of technology that we expect, or it may mean they are simply not trying to reach out. Another possibility is the sheer distance. The galaxy is so incredibly large. Even if a civilization were broadcasting signals, they might not have reached us, or they may be too faint for our current instruments to detect. Light takes time to travel, and so does any form of communication. If another world is 1,000 light years away, a broadcast would take that long. A powerful broadcast would take 1,000 years to arrive. Our reply would take another 1,000 years to go back. In that sense, conversations across the stars may be happening, but they are happening on timescales beyond our ability to notice. Humanity has been using the radio for just over a century. This is a mere blink of an eye compared to the age of the universe. It may be that civilizations exist, but their windows of communication are brief. A species might develop technology and broadcast signals for a short time. Then they could disappear due to war, environmental collapse, or some other disaster. If this pattern is a common one, the galaxy could be filled with ruins. These would be ruins of civilizations that no longer exist. We might simply be unlucky, living in an era when no one else is speaking. The stars live and they die over billions of years. They create the heavy elements that make life possible. But their deaths can also sweep clean the regions that are around them. Planets can be scorched, and their atmospheres can be stripped away. Any life that had existed there may be completely erased. Civilizations too may face their own versions of this cycle. Their progress may be followed by a decline. It is possible that the silence is not because life has never existed. It is because life has always been a fragile thing. It rises only to fall again before it could spread far enough to be noticed. Perhaps advanced civilizations do not reveal themselves because they choose not to. This is sometimes called the zoo hypothesis. The idea is that older, more advanced beings might be watching us. They watch us without making any contact, allowing us to develop. They allow us to develop without any interference. This is much as humans observe animals in the wild. If this is true, then the silence is not an absence, but a choice. Another suggestion is that civilizations may stay quiet out of fear. They may fear attracting any unwanted attention. In a universe where resources are limited, broadcasting your location could be dangerous. The silence in this view may be a form of survival. On the other hand, there is the chance that intelligence itself is rare. While simple life may be common, the leap to complex beings is unlikely. The leap to thinking beings might be so unlikely that Earth is one of the only places. It may be one of the only places where it has ever happened. We know that for most of Earth's history, life remained very simple. Multicellular organisms appeared only after billions of years. Intelligence, tool use, and technology came even later. In the vast sweep of evolutionary time, they may be brief and unusual phenomena. If this is the case, then we may be the exception rather than the rule. The Fermi paradox does not offer any easy answers. That is what makes it so incredibly powerful. It forces us to confront not only if we are alone, but what it means if we are. A universe filled with silence could mean that we are the first. We may be stepping into a vast cosmic arena with no one else yet present. Or it could mean that others came before us and they are now gone. Their traces have been erased by time and distance. In both cases, the emptiness of the skies becomes a powerful reminder. It is a reminder of our own fragility. New telescopes may soon give us some new clues. They are capable of scanning exoplanet atmospheres for the signs of life. Astronomers are beginning to look for more than just radio signals. They are looking for what are called technosignatures. This is any evidence of technology such as unusual energy use. It could be a strange pattern of light or even massive structures around stars. Each new method adds to our ability to test the paradox. If we find even the faintest hint of another civilization, it would change everything. If we find nothing, then the silence itself will only grow louder. It will press us to wonder why the universe so vast and ancient seems ours alone. The great filter why civilizations might always expire. By the laws of probability alone, there should be countless societies. They should be spread across the galaxy. Yet when we look into the night sky, we see only silence. The great filter is one possible answer. It suggests that at some point, life hits a barrier it almost never crosses. A civilization may rise, but something prevents them from lasting long enough. They are prevented from spreading to the stars. To understand this idea, imagine the history of life as a series of hurdles. The first hurdle is the origin of life itself. On Earth, it happened quickly. It happened perhaps within a few 100 million years after the planet cooled. But we don't know how easy that step really was. It could be common everywhere, or it might have been an incredible stroke of luck. After life begins, the next hurdle is complexity. For billions of years, Earth was covered only in simple, single-celled organisms. Multicellular life took an extraordinarily long time to appear. This is the kind that can build a body and a brain. Then comes intelligence. Dinosaurs ruled the Earth for over 150 million years. They did so without ever building a tool or a language. Intelligence may be far from inevitable, and even if intelligence evolves, the leap to technology is another hurdle. Many species are smart, but only humans built cities and spacecraft. The great filter could exist at any one of these stages. If it lies in the past, it means we are among the rarest of the rare. Life may be common, but an intelligent technological being might be non-existent. In that case, our existence would be a miracle of cosmic luck. But if the great filter lies ahead, the picture changes. That would mean a civilization like ours often reaches a certain level of development. They reach this level only to destroy themselves or collapse. They collapse before becoming interstellar. If that is true, then our future may be far shorter than we hope. The idea becomes even more unsettling when we think about the kind of filter. What kind of filter might exist in the future? One obvious possibility is self-destruction. An advanced society eventually creates technology powerful enough to end them. On Earth, nuclear weapons are a clear example. For the first time in history, humanity has the ability to destroy itself. It could do so in a single day. Other dangers lurk as well. Artificial intelligence, if not controlled, could outgrow us. A bioweapon could spread uncontrollably. Climate change could destabilize an entire ecosystem and society. The Great Filter may not be a single event. It may be a web of risks that multiply as a civilization advances. Another possible filter is a resource collapse. A civilization might depend on a limited supply of energy or raw materials. As they grow, they could strip their planet bare, unable to sustain themselves. Our own world offers a hint of this. Forests vanish, oceans, heat and minerals are dug from the earth. They are taken faster than they can be replaced. A society that cannot balance growth with sustainability might burn out quickly. They would leave little trace behind. From the viewpoint of the universe, an entire civilization might rise and fall. This could happen in the blink of an eye. A cosmic danger could also play a role. A supernova, a gamma-ray burst, or an asteroid impact can erase a world. This can happen in an instant. On Earth, life has survived many mass extinctions, but intelligence and civilization are fragile. A single catastrophic event might be enough to reset a planet's progress. It could reset it back to zero. If such a disaster strikes, often few civilizations would have time. They would not have time to grow beyond their home planet. The Great Filter could even be a matter of distance and time. A civilization might survive, but space is vast. The stars are spread so far apart that contact becomes almost impossible. A radio signal fades, and a spacecraft crawls across the void. It moves at a speed far too slow to bridge a galaxy. Perhaps many civilizations exist, but none ever meets. Each one is like a flickering candle in the dark. It is bright for a while, then gone, with no chance to find its neighbor. If civilization was common and long-lasting, we should see evidence. We should see massive engineering projects, colonized planets or signals. The fact that we do not suggests that something cuts them short. Either they rarely get started, or they do not survive long after they begin. For us, the Great Filter is not only a scientific puzzle, but also a mirror. If it lies ahead, then we are racing toward it. Even now, every new technology we create could be a doorway. It could be a doorway to our survival or our destruction. The filter could take the form of a choice we make. It depends on whether we learn to live wisely with our power or fall victim to it. There is another way to see the Great Filter. It can be seen not as a sentence, but as a challenge. If most civilizations do not survive, then perhaps survival requires an effort. It requires an extraordinary effort. It may demand cooperation on a scale rarely achieved. It may demand an innovation that allows a species to step off its fragile planet. If so, a species could spread into space. In this view, the filter is not impossible to pass, but very, very hard. Most societies fail, but a few succeed and endure. If we want to be one of those few, we will need to recognize the risk. We will need to act with care. The thought is sobering, but also motivating. The Great Filter reminds us that a civilization is not guaranteed to last forever. They are a fragile, temporary thing in a dangerous universe. But it also suggests that the future is not fixed. The filter might still be ahead, but it does not have to claim us. Our survival may depend on how we use the knowledge we have. It depends on whether we can learn to balance growth technology and our world's limits. And so the great filter hangs over our story like a shadow. It might be a relic of the past already behind us. It might lie in the future waiting to test us. Or it might take many forms spread across the path of any civilization. It could affect any civilization that dares to grow. In all cases, it speaks to the mystery of why the universe seems so quiet. It also speaks to whether we will find a way to keep our own light burning. Life's existence in the galactic graveyard. Is the universe too harsh for complex life? A planet and a galaxy like ours seem like the natural nursery of life. They are full of energy and materials for growth. But when we turn our eye to the older, quieter regions of the cosmos, the picture changes. These are the galactic graveyards. Here, the universe reveals a much harsher face. A galaxy that once blazed with bright stars now fades into a dim collection. It becomes a silent collection of ancient suns. Gas and dust, the fuel needed to make new stars and planets, has thinned out. Instead of a landscape of birth and growth, we find a realm of ending. We find a realm of survival under extreme conditions. Can life, especially complex life, truly exist in such an environment? A galaxy in its younger days is rich in gas and dust. This is the raw material for stars, planets, and the heavy elements life requires. These elements, carbon, oxygen, nitrogen, and others, are forged in stars. They are spread through space when those stars die. In a young galaxy, the cycle of star birth and death creates an ever-renewing supply. It creates a supply of the chemistry that life needs. But in a galactic graveyard, this process slows and eventually stops. With fewer new stars forming, there are fewer supernovae enriching the galaxy. They cannot enrich the galaxy with heavy elements. Over time, the supply of fresh material dwindles. What remains is locked inside ancient stars or scattered too thinly to form new worlds. For life, this lack of resources poses a serious barrier. This is especially true for life that needs a planet with stable conditions. Even if a planet formed earlier in the galaxy's history, it faces a problem. The problem is the aging of its parent star. In an old galaxy, the stars that remain are often smaller, dimmer red dwarfs, or they are swollen, unstable giants nearing the end of their lives. A red dwarf burns for trillions of years, but they are far from hospitable. Many of them flare violently. They release radiation that could strip the atmosphere of a nearby planet. This radiation could sterilize its surface. A giant star, on the other hand, may offer warmth for a short while, but it is doomed to an unstable ending. It blows off its outer layers, leaving only a dense white dwarf behind. A planet orbiting such a star might survive physically, but its environment would change so drastically that maintaining life would be impossible. The calm, steady sunlight that complex life seems to need is rare. It is rare in these stellar graveyards. Radiation adds yet another layer of danger. In the active part of the universe, a galaxy is bustling with energy, but much of it is balanced by fresh star formation and protective magnetic fields. In a dead or dying galaxy, conditions can be very different. A supermassive black hole often lingers in the center of these galaxies. The galaxy itself may be quiet, but the black hole can erupt. A stream of high-energy particles and radiation can flood the surrounding region. This can sterilize an entire zone where a planet might exist. Without the constant churning of young stars and gas clouds, the galaxy is harsher. They cannot absorb and scatter this energy. The galaxy becomes a harsher environment for any fragile biosphere. Complex life, which depends on stability, would find survival nearly impossible. The chemical balance of the universe also shifts with age. An early galaxy often had stars poor in metals. Astronomers use this term to describe elements heavier than hydrogen and helium. As time passed, star formation enriched a galaxy with metals. This created the conditions for rocky planets like Earth. But in a dead galaxy, this enrichment comes to an end. This is due to the lack of ongoing star formation. Over trillions of years, stars burn through what remains. The galactic chemistry grows stagnant. A planet that might have been rich in the elements needed for life is rarer. If life ever began in such a galaxy, it would face a challenge. It would have to sustain itself in an environment where new building blocks are not replenished. Some might argue that microbial life simple and hardy could endure. This is possible. A microbe on Earth has shown a remarkable resilience. It has survived in boiling vents at the bottom of the ocean. It has also survived in frozen Antarctic deserts and even radioactive waste. Perhaps a similar life form could persist on a hidden ocean, a subsurface ocean of a planet or moon orbiting an aging star. But when we ask about complex life, the odds shrink dramatically. This is life capable of building an ecosystem, evolving intelligence, and forming a civilization. Complex life needs not just survival, but stability over long time scales. It needs a stable climate, a steady source of energy and protection from radiation. These are exactly the qualities missing in the graveyards of a galaxy. Perhaps the universe itself has set a natural limit on how far life can go. It could be that the very conditions that allow a galaxy to form also doom it. They also guarantee that it will eventually turn hostile. A galaxy may offer a golden age where life can rise and flourish, but this age is temporary. As the galaxy burns through its fuel, the window for complex life closes. It narrows and eventually closes. If this is true, it may help explain why we have not detected alien life. Perhaps they are as short-lived as the active phase of their galaxy. By the time we look for them, the star that once supported them is already fading. On Earth, it took billions of years for complex organisms to appear. It took even longer for intelligence to rise. If we had been placed in a galaxy already far along its path to death, there is an issue. There might not have been enough time for us to emerge. The star would dim, and resources would run out before we could emerge. This suggests that complex life may depend on more than the right planet and star. It may also depend on the right moment in cosmic history. Too early and the galaxy lacks the heavy elements to form an Earth-like world. Too late and the galaxy has already burned through its fuel. This leaves little room for growth. This paints a sobering picture. The universe may be filled with countless planets, but many of them may orbit stars in regions that have already gone quiet. To us, they would appear as ancient silent worlds. They would be unlikely to host anything more than a microbe clinging to survival. The grand story of life may not be written evenly across the cosmos. It may be tied to a certain epoch, a certain phase in the life of a galaxy. This is where the conditions align for complexity to arise. Outside of those windows, the universe may simply be too harsh. It may be too unstable and too empty of the resources needed for life to thrive. We live in a galaxy still alive with star formation. Its stars are stable enough to support life for billions of years. We are on a planet with just the right chemistry and balance. We may be the fortunate few living in one of the rare gardens. These are gardens where complexity can bloom. The silence of the galaxy may not mean life is impossible. It may only mean that life has a narrow window to emerge, and it may mean that most of the cosmos has already passed beyond it, a stellar remnant and the fate of a habitable planet. When a star like our Sun reaches the end of its fuel supply, it swells. It swells into a red giant. During this stage, the inner planets are roasted. In some cases, they are swallowed entirely. Earth itself will not survive this transformation. Its surface will be scorched beyond recognition. Eventually, the outer layers of the dying star drift away into space. They form a glowing planetary nebula. The dense core shrinks into a white dwarf. It no longer shines through fusion. Instead, it glows faintly as it cools over billions of years. For any planet that avoids being destroyed, the change is dramatic. This is during the red giant phase. Instead of basking in stable warmth, they orbit a fading ember. If life ever existed there, it would have to adapt to extreme cold and darkness. This task may prove impossible for a complex organism. For a more massive star, the story is even harsher. Their cataclysmic end can rip apart an entire planetary system. The shockwave and intense radiation obliterate any nearby planets. They strip atmospheres, boil oceans, and sterilize surfaces in an instant. What remains at the heart of the explosion is not a gentle neighbor. The intense radiation field around a neutron star is hostile. The violent gravitational pull of a black hole is also hostile. They make for a hostile environment for any surviving planet. Yet a planet does sometimes survive. Astronomers have detected a planet orbiting a pulsar. These so-called pulsar planets are some of the strangest worlds we know. They exist in an environment filled with deadly radiation. They are bombarded by high-energy particles. The fact that they are there at all is remarkable, but few believe such a place could support life. If anything, they stand as a grim reminder. They remind us that a planet can endure even when conditions make it uninhabitable. A white dwarf, on the other hand, may provide a glimmer of hope. It could provide hope for habitability, at least in theory. Because they cool slowly, they can provide a faint but steady source of energy. This can last for billions of years. If a planet is the right distance away, it could sustain liquid water. In fact, some astronomers have suggested that life might emerge around a white dwarf. This could happen long after most stars, like our Sun, have burned out. The catch is that a planet would need to migrate into this narrow habitable zone. This would have to happen after the star's transformation. Anything close to the star during its red giant phase would have been destroyed. Even then, the window of habitability may be limited. It is limited as the white dwarf continues to cool. It is a fragile balance. It is one that may rarely, if ever, produce stable conditions for complex life. When a galaxy runs out of the gas needed to form new stars, it becomes a graveyard. It becomes a cosmic graveyard filled with stellar remnants. Its sky would be dotted not with the brilliance of new stars. It would be dotted with fading white dwarfs, neutron stars, and black holes. The planets that remain would orbit a dead or dying sun. They would be bathed in cold and silence. Even if some of these worlds once had oceans, atmospheres, and perhaps life, those days would be over. Without new stars to form and new energy to feed ecosystems, the environment is hostile. The galactic environment becomes hostile to growth. In such a graveyard, the chance for life to persist grows vanishingly small, let alone thrive. The fate of a habitable planet then seems tied to cosmic decay. Every world that forms is given only a temporary lease on habitability. This lease is dictated by the lifespan of its star. It is also dictated by the changing conditions of its galaxy. For Earth, that lease is about 5 billion years more. This is until the Sun becomes a red giant. For a planet orbiting a massive star, the window may last only a few million years. This is a blink in cosmic time. Even a planet around a long-lived star eventually faces a decline. This happens as those stars grow old, expand, and leave only a remnant behind. And yet there is a strange persistence in the universe. While stars die and planets freeze, the material that supported life does not vanish. The carbon, oxygen, and nitrogen that once formed the building blocks of biology remain. They remain scattered across the galaxy. They may end up locked inside a cold white dwarf. They could be trapped in the crust of a rocky planet or drifting as dust. These elements can still play a role in a future cosmic cycle. This is true even if that cycle takes trillions of years to unfold. The graveyard of planets and stars is not entirely empty. They are filled with the raw ingredients of new worlds, and perhaps in some distant future new forms of life. The fate of black holes, will they evaporate or consume the universe? A black hole feels like an eternal trap. It devours everything that comes too close. and holds on to it forever. For much of modern astronomy, they were thought of as the ultimate full stop. They were an object that consumes but never gives back. But in the 1970s, a surprising idea shook that view. Stephen Hawking suggested that black holes are not completely black. Instead, they should give off a faint glow, a slow leakage of energy. That means even these monsters of gravity may one day vanish. This idea, called Hawking radiation, forever changed how we think. We changed how we think about the fate of black holes. With it, we changed how we think about the long-term future of the cosmos. To understand why, we need to picture the strange way the universe works. This is at its smallest scale. In the world of quantum physics, empty space is not truly empty. It bubbles with what are called virtual particles. These are pairs of matter and antimatter that constantly appear and disappear. Normally, these pairs cancel each other out almost instantly, leaving no trace. But near the edge of a black hole, the event horizon, something different can happen. One particle of the pair may fall into the black hole while the other escapes. To an outside observer, it looks as though the black hole has emitted radiation, and because energy must come from somewhere, the black hole loses a tiny bit of its mass. This process is unbelievably slow. For a black hole the size of our Sun, the time to completely evaporate is immense. It would take about 10 to the power of 67 years. This number is so vast it is hard to imagine. For the supermassive black holes at the center of a galaxy, the timeline grows. It grows to 10 to the power of 100 years or more. That is 100 billion trillion times longer than the current age of the universe. For now, a black hole looks eternal, but on the grandest timeline imaginable, they too may fade. The evaporation begins gently, almost imperceptibly. For billions of years, the black hole would remain stable, its pull unchanged. But as it grows smaller over an unimaginable span of time, the radiation intensifies. The black hole slowly warms, glowing more and more, until in its final moment it releases an enormous burst of energy. A black hole that once consumed stars would end its life in a brief but brilliant flash. It would evaporate completely in a final burst of light and heat. If this picture is correct, then the universe's most powerful engine is not eternal. It is not an eternal prison, but a temporary feature. Eventually, in the farthest future, we can imagine there will be no black holes left. Instead, the universe will be filled with only a faint radiation. It will be cooling and spreading endlessly. This paints a picture of a cosmos that not only grows quiet but also loses its darkest shadow. Yet, not everyone is certain this will happen. Hawking radiation has never been directly observed. The effect is far too faint for us to detect with current technology. Our best evidence for it comes from the mathematics of quantum theory and general relativity. These are two frameworks that are powerful but not yet fully reconciled. Some physicists suspect that our picture of a black hole may still be missing a piece. Perhaps black holes do not evaporate completely. Perhaps they leave behind a tiny, stable remnant. This would be an object that carries the last trace of their existence. Or perhaps our understanding of gravity itself will need to change. This change could alter this story. Another possibility is that black holes could play an even more active role. This would be in the universe's future. Instead of slowly vanishing, they may continue to dominate the cosmos. This would happen long after stars have burned out. As galaxies fade and stellar remnants drift apart, black holes will remain. They will remain as the last powerful anchor of matter. They could pull in a stray star, a planet, or even another black hole. They would merge into a larger and larger structure. In this view, a black hole may not fade away quietly. It may continue to reshape the universe deep into its dark future. Imagine a time trillions upon trillions of years from now. Stars have all gone dark, and galaxies have dissolved into scattered matter. Black holes would still lurk, swallowing anything that comes too close. A whole solar system could disappear into their depths. Even if evaporation does eventually win for a staggeringly long time, the universe could belong to them. Which picture is more likely? Will black holes eventually evaporate into nothing, leaving the cosmos empty? Or will they remain consuming stray matter and dominating the universe? The truth may depend on an aspect of physics we do not yet understand. Hawking radiation is a bridge between two great theories that do not always agree. To fully answer the fate of a black hole, we may need a deeper theory of everything. We need one that unites the small and the large. If black holes do evaporate, then the universe seems destined for a slow fading. It would be a total fading, with no structure left anywhere. If they remain, the cosmos may stay shaped by their presence far longer. Giant black holes would stand as the last monument of creation. Either way, the timeline is so immense that our own age of stars will look brief. Our age of stars and galaxies will look like a brief spark compared to what lies ahead. Cosmic zombies, the potential for resurrecting a dead star. A star burns through its fuel and transforms into a red giant. It collapses, explodes, or settles into a faint ember of its former self. The story seems complete, a line drawn under a chapter that can never be reopened. Yet there are always exceptions and strange phenomena. The idea of a star being revived or reanimated may sound strange, but the universe has shown hints that such a thing may not be impossible. A dead star in most cases is a white dwarf, a neutron star, or a black hole. For a long time, these endpoints were seen as permanent. Nothing could bring a star back from such a fate. But over time, observations revealed that sometimes these corpses do not rest quietly. They can interact with their surroundings in a violent, unpredictable way. This makes them look like they've come alive again. One of the most well-known examples comes from a white dwarf in a binary system. A white dwarf may sit next to a still living companion star. It quietly orbits invisible against the glare of its partner. But as the companion evolves and expands, gas from its outer layers can spill over. This flow of fresh hydrogen piles up on the white dwarf's surface. It eventually ignites in a sudden nuclear burst. The white dwarf flares into brilliance, creating what astronomers call a nova. To an observer, the dead star appears to wake from a slumber. It shines with a newfound energy. In truth, it has not been reborn in the same sense as a young star, but the outburst is dramatic enough to make it appear resurrected. These nova events can repeat many times. This is as long as the white dwarf keeps stealing fuel from its companion. Even more dramatic are the cases where a white dwarf gathers too much material. If it crosses a critical mass limit, the star can no longer support its own weight. At that point, it collapses and explodes in a supernova. It leaves nothing but scattered ash behind. This is not so much a resurrection as it is a final catastrophic blaze of glory. Still, it shows that even a star thought to be dead can find a way to burn again. It can burn if only briefly and in a spectacular fashion. A neutron star too sometimes behaves like a cosmic zombie. A neutron star may spend millions of years quietly spinning. Its magnetic field fades and its energy slowly leaks into space. Then, through some unknown trigger, it can suddenly flare to life. A magnetar, which is a special kind of neutron star, is famous for this. These objects unleash powerful bursts of radiation. They can outshine an entire galaxy for a few moments. It is as if the star long thought to be fading suddenly shakes itself awake. The cause of these flares is still debated, but many scientists believe they result from the magnetic field twisting and snapping. This releases an enormous amount of stored energy. Sometimes a neutron star can also switch on as a pulsar. Some pulsars are known to stop emitting and then start again. This can happen after a year or even a decade. It is almost as if the star fell into a deep sleep and then reawakened. Why this happens is still a mystery. But such behavior reinforces the idea that death in the cosmos is not always absolute. Sometimes there is a second act. Perhaps the most eerie resurrection happens when a neutron star merges. It may merge with another neutron star or a black hole. In these collisions, a titanic force rips apart matter. It releases a burst of energy so intense it can be seen across billions of light years. The gravitational waves from such an event ripple through space-time itself. These explosions create heavy elements. In a sense, the neutron star is destroyed, but what follows can be seen as a new creation, the birth of elements. It is the stirring of matter into a new form. What died has given rise to something new. Some astronomers wonder whether black holes themselves could one day spit out energy. This might resemble a star's rebirth. Hawking radiation suggests that a black hole can evaporate over an unimaginable time, but in its final moments, as it shrinks to nothing, it may release a burst of energy. To a distant observer in that far future, it might look like the last flare. It would be the last flare of a star that has long since been gone. It would not be a true resurrection, but the echo of one. It would be the last heartbeat of something that defied death for an eon. There are also stranger ideas not yet proven that keep the discussion alive. Some physicists have proposed that a dead star could capture enough gas or dark matter. It could reignite nuclear fusion in its core under certain exotic conditions. If this were possible, it would mean a star could start shining again. It could shine after billions of years of silence. Such an event, if it ever occurs, would be unimaginably rare. We may never witness one, but in a universe as vast as ours, even a rare thing can sometimes find a stage. The line between life and death in the cosmos is not always sharp. A star does not simply vanish into nothingness when its fuel runs out. They leave behind a remnant that can still interact, flare, or even explode. This happens under the right circumstances. A white dwarf stealing gas, a neutron star pulsing again, a black hole releasing its final breath. Each of these is a kind of resurrection, even if only partial or temporary. The universe is full of objects that should be dead, but somehow they still find a way to stir, shine, and even terrify. Death in the cosmos, as in life, is often more complicated than it first appears. In the cold graveyard of a galaxy where stars should lie in silence, there may still be echoes. There may still be an echo of light, a flicker of energy, and a whisper of resurrection. The role of rogue planets in a dying universe. When a star dies, its planets often face destruction. Some are swallowed as their sun expands. Others are frozen in the darkness once the light of their star goes out. But not all planets are tied forever to their parent system. Some are cast loose, ejected from orbit by the chaotic dance of gravity. Or they are flung into the void when a star dies or is torn apart. These lonely wanderers are called rogue planets, worlds without a sun. They drift through space with no steady source of light or warmth. A rogue planet has been seen as a curiosity, hidden and faint. They are almost impossible to detect against the black background of space. Yet when we imagine the distant future of the universe, they take on a new role. This is a time when stars are long gone. They may become the last survivors of the cosmos. They may still carry with them a shadow of complexity in a silent universe. In the youth of a galaxy, when stars and planets are forming, gravity is powerful. It can be as much a destroyer as a builder. A young star often forms in a cluster, tugging at each other. This disturbs the orbits of newborn planets. A close encounter with another star can sling a planet out of its system. It can free it from its sun. The planet does not disintegrate. It simply carries on traveling through space forever. Later in cosmic history, when a star grows old and unstable, it can eject planets. A red giant star swelling outward can destabilize an orbit. A supernova explosion can rip an entire system apart, sending planets flying. By these and other means, countless planets are set free. They become wanderers in the cosmic wilderness. Some estimates suggest there may be more rogue planets than stars in our galaxy. 1 billion upon 1 billion of them drifting in silence. For most of their existence, a rogue planet is dark, cold, and nearly invisible. Without a star to heat them, their surface plunges into a deep freeze. To us, they may seem like lifeless rocks or frozen gas giants wandering aimlessly. But under their icy shell, there may be a secret. A planet with a thick atmosphere could trap some heat. A large planet with internal radioactive decay might sustain warmth deep inside. Most intriguingly, a rogue planet with a subsurface ocean could harbor liquid water. This would be protected under kilometers of ice, shielded from the void outside. On Earth, we know that life can exist without sunlight. It thrives instead around deep-sea vents powered by the planet's heat. If something similar could exist on a rogue planet, these worlds might not be barren. They could be the hidden sanctuaries of life in a universe where stars burn out. Imagine a universe tens of trillions of years from now. Galaxies have spread apart so much that light from one cannot reach another. By then, most stars will be gone. The small, dim stars that live the longest will have exhausted their fuel. White dwarfs, neutron stars, and black holes will be all that remains. Yet a rogue planet once cast loose will still exist. Unlike a star, they do not rely on fusion or radiation to survive. They are inert, long-lived, and resilient. They are a fragment of the old universe drifting endlessly. The cosmic stage around them grows colder and darker. Where once galaxies blazed with 1 trillion suns, the future may hold only embers. The distant future may hold only scattered embers and a wandering planet. In this way, a rogue planet is not just a survivor of stellar death. They are a survivor of cosmic death. Their significance lies not only in their endurance, it also lies in what they might carry with them. A rogue planet could serve as a vessel preserving complexity or even life. It could preserve them long after stars are gone. A civilization, if they still existed, might cling to such a world as a refuge. An advanced being could hollow out the crust of a rogue planet. It could tap into geothermal energy to create an artificial warmth. They could shield themselves beneath a thick ice. They would be protected from cosmic rays and the vacuum outside. Such an existence would be far removed from the bright open world we imagine today. But in a dying universe, survival might mean adapting to the cold and dark. A rogue planet would be among the last possible homes. There is another role a rogue planet may play. As a galaxy ages and stars fade, gravitational interactions may still continue. A rogue planet could be captured again. It could be pulled into an orbit around a stellar remnant or a black hole. In that case, it might briefly become part of a new kind of system. It would orbit in an eternal night around a collapsed star. Such a capture would be rare in the vast emptiness of space. But a rogue planet could still participate in the last dance of matter. Even in decline, gravity does not stop weaving new patterns. In the deep future, as black holes evaporate, a rogue planet would continue its journey. Even as the last trace of starlight vanishes. They are not indestructible, of course. Given enough time, their atoms themselves may decay depending on physics. But on a time scale beyond comprehension, they will persist. They will persist longer than the stars that once gave them birth. In the silence of the far future, a rogue planet could drift alone. It would drift through the void carrying the memory of a once bright universe. If life ever found a way to cling to such a place, they could be more. A rogue planet could represent not just the last physical survivor, but the last living one. They would be both a tombstone and an ark. They would show that the cosmos, no matter how bleak, never loses all complexity. It does not lose it in one final instant. Instead, it fades slowly, piece by piece. It leaves scattered worlds to drift in the dark. The story of a rogue planet is the story of resilience, It is a story of a fragment of creation that outlasts its creator. And in the endless night of a universe approaching heat death, they may be the last spark. They may be the last spark of a forgotten age, a dark matter, and an invisible graveyard. Dark matter has always been a silent player in the story of the universe. Unlike a star which shines and dies in a dramatic explosion, or a galaxy which sweeps across the heavens with a billion suns, dark matter does not call attention to itself. It does not glow, it does not radiate heat, and it does not interact with light. Yet it holds the cosmos together. It acts as the scaffolding on which a galaxy forms and lives out its life. Without dark matter, the familiar structures of the universe would never exist. And long after the last star has faded, dark matter will still be there. It will be an invisible skeleton of reality stretching across the cosmic graveyard. In the early universe, dark matter shaped the first galaxies. It clumped together under gravity, forming an invisible well. This well pulled ordinary matter in. Over time, stars lit up inside these wells and galaxies were born. But when those galaxies eventually run out of fuel, dark matter remains. When their stars burn out, it remains. It does not die or decay in the same way as ordinary matter. Its presence continues vast and hidden. It silently guides the motion of whatever is left. If the universe becomes a place of cold, faint remnants, a black dwarf, a neutron star, a black hole, dark matter will still surround them. It will stretch across empty distances and tie them together into an unseen web. Scientists still do not know what dark matter really is. It could be a particle unlike anything we have detected. It could be something stranger, a field or an effect we barely understand. But what makes it important for the story of the far future is its persistence. A star can burn out, a galaxy can drift apart, even a black hole can evaporate over an unimaginable timescale. Dark matter, however, may endure without a limit. If it does, then it will be the last great structure of the cosmos. It will form the framework of a universe otherwise emptied of energy and light. Imagine looking out into a darkness and seeing nothing, but know that beneath that black canvas a vast halo of unseen material is still there. It no longer holds a glowing star, but it continues to curve space. It bends the path of an object and defines the architecture of emptiness. The great cosmic web, once so beautifully lit by galaxies, will still exist. It will be a ghostly web made only of what cannot be seen. The role of dark matter in such a time becomes even more fascinating. In an expanding universe driven apart by dark energy, dark matter is the counterweight. It is the part that resists dispersal and clings to itself through gravity. Even as galaxies fly farther apart, each one remains wrapped in its cocoon of dark matter. This means that while the grand structure of the cosmos will vanish from view, smaller systems may remain. They may remain bound together for much longer. A cluster of collapsed stars, black holes, and perhaps wandering planets could orbit. They could continue to orbit within a dark matter halo, holding onto each other. These could be the last islands of structure surrounded by an ocean of nothing. But what happens to dark matter itself? Does it last forever? Some scientists wonder whether dark matter could decay over a very long time. If so, then even the invisible skeleton of the universe might crumble away. But no evidence yet suggests that this is happening. The best we know, dark matter has remained stable since the beginning of time. There is little reason to think it will vanish anytime soon. If it truly endures without a limit, then the final universe will not be empty. It will still have this strange, invisible substance stretched across its depths. It will be a faint shadow of the universe's younger self. There would be no light, no heat, and no stars to see. Yet gravity would still move things. An invisible halo would continue to guide the path of the last remnants. A black hole would glide slowly through space. A rogue planet would wander endlessly, and a dust cloud would drift in nothingness. Without dark matter, even these leftovers might drift apart more quickly. But because of it, there could still be some structure. Even in the deepest silence of time, the cosmic graveyard would not be flat. It would still have a faint outline of its old skeleton. One way to imagine this is to think of a great cathedral, a cathedral that has lost its roof, its stained glass, and its candles. The stone arches remain, but they are empty and silent. Dark matter is like those arches. It is the shape that remains after the light is gone. It is the unseen structure that gives form to the void. To walk among it would be to wander in a world where everything is hidden, where the skeleton of creation is all that is left. There is also a strange possibility about dark matter's final role. It could be the final foundation for whatever form of life might arise in the deep future. If energy is scarce, could some unimaginable life form learn to use it? Could it learn to use the invisible substance itself? This is far beyond our understanding, but it is a thought that lingers when we consider how often life has surprised us. Just as the first microbes once fed on chemical energy in rocks, this was long before plants and animals existed. Perhaps the distant future could hold a being that lives in a way we cannot imagine. It might draw sustenance from what looks to us like nothing at all. If that ever happens, dark matter would not just be a skeleton of the universe. It would be its last hidden well of possibility. For now, all we can do is wonder. Dark matter is invisible to our eyes and instruments except through its gravity, yet its importance cannot be overstated. It is the silent architect of galaxies, the hidden thread of the cosmic web, and possibly it is the last survivor of all. When the rest of the universe has faded away, the future seems silent and cold, but perhaps it is more accurate to say that it will become invisible. Dark matter will still be there, a cosmic graveyard beneath the surface. It will hold up a universe that to us would look like nothing at all. Beyond the observable universe, the cosmic graveyard we will never see. Our observable universe is a bubble with a finite radius. Beyond it lies a vast expanse we will never be able to witness. Even with the most powerful telescope, we cannot cross this horizon. Even with billions of years of patient observation, the edge of the observable universe is a horizon we cannot cross. And yet, beyond this horizon, the universe continues. Entire galaxies, clusters, and cosmic structures live, age, and die in silence. They are hidden forever from human eyes. We know that the universe extends farther, but its contents are inaccessible. Over time, cosmic expansion continues to accelerate. This is due to the push of dark energy. More and more galaxies slip past this horizon. Once gone, their light can never catch up. They vanish from our sight forever. From our point of view, it is as though the universe is slowly erasing itself. They may be some of the richest parts of the universe. They could be filled with galactic giants, star-forming nurseries, and massive black holes. Yet they will all eventually undergo the same fate as the region we can see. Stars will burn through their fuel. Supernovae will scatter elements into space. Black holes will consume matter before evaporating over an unimaginable timescale. Without new energy to replenish them, these faraway galaxies will fade into silence. What makes this tragedy greater is that we will never witness their final act. They are lost to us. They are separated not by distance alone, but by the very laws of physics. Our universe may be far older and stranger than what we can observe. If there are regions beyond our horizon that evolve differently, they could be unique. They could be home to cosmic events we cannot even imagine. An entire epoch of star formation, galactic collision, and stellar death could be playing out. It could be happening endlessly with no record that will ever reach us. There could be an entire cluster where stars burned faster and died earlier. They would leave nothing but cold remnants. To us, they are beyond existence. The accelerating expansion of the universe makes this separation worse with time. In the far future, even the galaxies we see today will slip into invisibility. Eventually, only our local group of galaxies will remain in sight. All else will vanish beyond the horizon. This will leave us stranded in a dark, lonely pocket of space. This means that a future observer will live in a universe that looks smaller. This would be an observer billions or trillions of years from now. For them, the cosmic graveyard will not only be unseen but also unknown. But what if we think of it differently? Beyond the horizon, galaxies are not only fading but also being born. We cannot see them, but they must exist. A new star ignites, a new planet forms, a new possibility emerges. If life exists in those unreachable realms, it will evolve under a sky we will never know. An entire civilization may rise and fall in isolation. They will be unaware of us, just as we cannot be aware of them. Each is trapped in its own cosmic bubble. They are separated forever by the expansion of space. This gives the universe a strange dual character. It is both vast beyond comprehension and limited by the boundary of observation. No matter how advanced a civilization becomes, no technology can pierce the veil. No telescope can see beyond the observable universe. The speed of light is not just a challenge, it is a fundamental barrier. This means that some mysteries are permanent. The unseen graveyard of distant galaxies will remain invisible. This is not because we lack a tool. It is because the universe itself forbids us from ever reaching them. Even so, the mind reaches outward. Scientists speculate about what lies beyond based on what we see inside our bubble. A pattern of structure, the distribution of galaxies, and the laws of physics suggest things. They suggest the universe beyond our view must look much the same. But this is still an assumption. There may be surprises, a vast region where matter is arranged differently, a region where expansion has unfolded in a unique way, or a region where an unknown force has left its mark. The graveyard of those galaxies may not follow the same timeline as ours. Perhaps the true death of the universe is already unfolding beyond our reach. Maybe an entire region has already grown cold and lifeless. Stars would be gone, and black holes would have evaporated. If so, then the end of everything is not a distant possibility. It is a present reality, creeping inward from an unseen corner of the cosmos. In that case, the observable universe is like a shrinking island of light. It is surrounded by an ocean of darkened ruins. A graveyard reminds us of the passage of time, of a story completed. It reminds us of an ending that shapes a meaning. The cosmic graveyard beyond our sight is no different. They remind us that the universe is not eternal in the way we might wish. They reveal that even in infinity loss exists. Each unseen galaxy is a reminder that all things end. This is true even if those endings are hidden. The heat, death of the universe, a cosmic funeral. In the farthest stretch of time imaginable, there waits a final chapter. This is beyond the lifespan of stars, beyond the collapse of galaxies. It is beyond the last black hole evaporating into nothingness. It is the idea of the heat death of the universe, the ultimate cosmic funeral. Unlike the violent explosion of a supernova, this ending comes quietly. Unlike the sudden collapse of a dying star, this ending is gradual and inescapable. It is not one event, but the sum of countless processes slowly winding down. This continues until the universe no longer has the ability to change. To picture this end, we must imagine a time stretched out to a vast length. Even 1 trillion years becomes an insignificant stepping stone on the way to emptiness. The concept begins with the second law of thermodynamics. At its core, this law tells us that energy naturally spreads out. It moves from a concentrated, useful form into a more disordered, unusable one. In the universe today, stars shine because they are hot, compact furnaces. They are furnaces of energy surrounded by the cold vacuum of space. That difference between hot and cold makes an energy flow possible. It lets stars burn, planets orbit, and life exist. But over time, as stars die and energy is used up, the difference grows smaller. Energy spreads more evenly across space. Slowly, the contrast that drives activity fades away. Without a contrast, nothing moves, nothing shines, nothing lives. To see how this unfolds, we can walk forward through the deep future of the cosmos. First, stars like our Sun exhaust their fuel and fade. For a time, galaxies continue to sparkle with the light of younger stars. But over billions of years, these too reach their end. Star formation slows, then stops. The great spiral arms of a galaxy, once bright and full of energy, dim into a shadow. What remains are the remnants, a faint ember of a white dwarf, a cold neutron star, and the invisible mouth of a black hole. Even in this stage, the universe is not yet dead, only aging. Energy still exists in a concentrated form. It is locked inside matter, swirling within a black hole or lingering as radiation. But as time marches forward, even these reservoirs begin to drain away. A white dwarf, once glowing faintly, cools over trillions of years. It cools until it vanishes into an invisible black dwarf. A neutron star may persist as a silent sphere of dense matter, but with no heat or light to give, it becomes a frozen monument. A black hole, though seemingly eternal, is not immune either. Through the slow process of Hawking radiation, it evaporates. It shrinks into nothing over a timescale that dwarfs the lifespan of any star. As these structures fade, the universe begins to smooth out. Energy, once clumped into stars and galaxies, spreads more evenly. Without a new source of concentrated power, there is nothing left to restart creation. Galaxies, empty space grows darker, and the silence deepens. The universe enters what is sometimes called the dark era. All that remains is a thin trace of radiation, scattered particles, and expanding space. The expansion of the universe only adds to this decline. With every passing epoch, galaxies drift farther apart, stretching space. Today we can see billions of galaxies across the cosmos, but in the distant future, most of them will slip beyond the cosmic horizon. They will be pulled away faster than light by the expansion of space itself. For an observer living trillions of years from now, their universe will look smaller. It will be limited only to the remains of their local galaxy. This is if even that survives as a coherent structure. The grand view of the cosmos filled with billions of lights will vanish. As the universe ages into this distant future, its temperature drops. The cosmic microwave background, the faint afterglow of the Big Bang, will cool further. It is already chilled to just a few degrees above absolute zero. Over time, it will thin until it is indistinguishable from darkness. The very fabric of the universe will approach absolute zero. This is the lowest temperature possible, where particles barely move. No energy can be extracted. The most haunting aspect of the heat death is not that energy disappears. It never truly vanishes. It is that it becomes useless. Energy evenly spread across space cannot do work. It cannot flow from one place to another. It cannot be harnessed to power a star or a life. In this sense, the universe dies not in a violent end, but in a quiet exhaustion. All the drama of creation was only a brief spark. The fiery birth of stars, the collision of galaxies, the explosion of supernovae, these were all brief compared to the endless calm that follows. If the universe inevitably drifts toward this final frozen state, then all structure is temporary. Everything we see today, from galaxies to living beings, is a temporary pattern. It is a pattern in an ocean that will one day be flat and still. Some thinkers find this vision bleak. It is a story where even the greatest achievement fades into silence. Others see a beauty in the idea that we live during the universe's brief brilliance. We live in a time when stars still shine and life can still exist. the heat death becomes not just an ending but a reminder. It is a reminder of how precious the present truly is. Even so, some scientists wonder whether the heat death is truly inevitable. Could unknown physics alter this picture? Might the universe cycle back into a new beginning? Or could dark energy itself change over time, shifting the fate of everything? These questions remain open. For now, the heat death stands as the most widely accepted view of the far future. It is a story rooted in the laws of thermodynamics and the slow unfolding of entropy. To imagine the heat death is to imagine a silence stretched across an infinity. It is the ultimate graveyard not of a single star or galaxy but of everything. Yet in contemplating it, we also glimpse the remarkable truth of the present. We are here in a cosmos, still full of light, still alive with energy. We are here in a cosmos, still capable of wonder. The funeral may come, but for now the universe still sings. The end of information. Will the universe forget its own past? In the beginning, the universe was a place overflowing with information. Every particle, every photon, every interaction carried a record of what came before. The afterglow of the Big Bang is an imprint of the infant universe. It is still visible as the cosmic microwave background. The pattern of galaxies, the motion of stars, and even the isotopes inside planets tell a story. They tell a story of processes that took place long ago. In many ways, the universe is a library written in matter and energy. Each structure contains a page of its history. But like any library, a page can be damaged, ink can fade. Over a great enough stretch of time, even the strongest record can be lost. Information in physics is not just knowledge, it is tied to the very arrangement of matter and energy. When a star forms, its light is a kind of signal carrying information. It carries information about its temperature, its mass, and its age. When it explodes as a supernova, it sends out a final message. This message is in the form of radiation and heavy element. These are pieces of data the universe distributes freely. The same is true for a black hole, a galaxy, and even the faint whisper of radiation. Each moment is a record. But as the universe ages, these records begin to disappear. In every direction, the clarity of the cosmic story begins to blur. The expansion of the universe is the first great eraser. As galaxies move farther apart, their light stretches into longer wavelengths. Eventually, the glow of a galaxy beyond a certain distance will redshift into invisibility. To an observer far in the future, it will appear as if those galaxies never existed. Their information is not destroyed immediately, but it becomes unreachable. From a local point of view, the universe looks emptier. It is stripped of the pages that once told of its vastness. A black hole complicates the picture further. According to classical physics, anything falling into a black hole disappears forever. Its information is sealed away. This created a deep paradox. Does the universe lose data whenever a black hole swallows it? Quantum physics suggests otherwise. Hawking radiation proposes that a black hole slowly releases radiation. This radiation encodes in some scrambled form the information it once trapped. If true, then information is not destroyed but transformed. It is scattered back into the universe in the faintest whisper of heat. Yet this process is unimaginably slow. And even if information eventually leaks back, it is so scrambled, it may never be reconstructed. The story it once told would be effectively erased. It would be replaced with a noise too faint to interpret. Entropy is the ultimate archivist in this story. As time marches forward, the universe tends toward an equilibrium. Differences in temperature, pressure, and energy even out. Entropy does not destroy information outright, but it makes it harder to access. Imagine a book shredded into pieces and scattered in the wind. In theory, the information is still present in the fragments, but the effort required to piece it back together grows impossible. The same is true for the cosmos. Over trillions upon trillions of years, particles will drift farther apart. Energy will spread more evenly. The record of past events will dissolve into a pattern that no longer reveals its origin. Information becomes unrecoverable not because it vanished, but because it is lost in the noise. One of the strangest possibilities is that even the laws of physics may not be eternal. If constants change, if space-time itself decays, then the framework could crumble. The framework that defines what information means could crumble. What would it mean for the universe to forget not just the arrangement of particles? What if it forgot the rules that gave those arrangements an order? The cosmic library is not written in stone. It is written in a pattern that depends on the fabric of reality itself. If the fabric frays, the writing disappears. Some thinkers wonder whether the universe itself is a kind of computer, a computer processing information at every moment. If so, then the end of information would be like shutting down the last machine. When energy differences vanish and particles no longer interact meaningfully, nothing is left. There is nothing left to compute. The memory of the universe becomes frozen, unchanging. There would not even be the faint activity of a new event to add to its record. In this view, the universe does not just forget its past. It stops thinking altogether. For billions of years, existence has been a conversation between matter, energy, and time. Stars burned their message across the sky. Galaxies formed a grand pattern, and life itself arose as a complex reader. Life was a reader of the cosmic text, but all stories move toward their end. In the distant future, when the last black hole has evaporated, the record will be gone. When the last particle drifts silently in the void, the universe will hold no memory of the Big Bang, no trace of the galaxies. It will hold no echo of a life. The library will be empty, the pages blank. The night sky is a museum of information. It offers a glimpse into billions of years of history. Every photon is a message from the past, still legible, still carrying a meaning. Perhaps this is the gift of our time. We exist in an age when the library is still open and the story is still there. A dimensional decay will the fabric of reality unravel. Space feels like a container and time feels like a flow. But what if these are not a permanent fixture? What if the very framework that makes existence possible is subject to decay? In the far reach of time, the universe may face a stranger kind of end. This is long after galaxies have dimmed and stars have turned to ash. The end could be the fading of dimensions themselves. This is the idea of dimensional decay. The fabric of reality does not just stretch or cool but begins to unravel. The thought seems almost impossible at first. Space has always been three-dimensional, at least as far as our experience goes. One can move left and right, forward and backward, up and down. All of physics is built upon this foundation. Add in time as a fourth dimension, and you have the stage on which every star has burned and every atom has collided. But a theory in physics suggests that dimensions may not be fixed. They may not be fixed in number or stability. In fact, some models of the early universe suggest that extra dimensions existed. They might have existed only to collapse or curl up into a tiny hidden form, a form too small for us to see. If a dimension can appear or shrink away, perhaps they can also decay. They could collapse again in the deep future. This raises the strange possibility that the universe may not simply run out of energy. It may not collapse into a singular point. Instead, it may lose the very scaffolding that makes matter and energy possible. Imagine a sheet of cloth stretched across a frame. At first, it holds its shape smooth and firm. Over time, though, the threads begin to loosen. The weave unravels. Eventually, the fabric ceases to exist as a surface at all. It is only a scattered thread with no pattern. In the same way, reality might lose its dimensional weave. Space itself could become undefined, with no direction in which matter could move. This kind of decay would be a quiet dismantling. A galaxy, if any remained, would find that the distance between its stars was no longer meaningful. an atom might no longer be able to hold together. This is because the space in which its particles interact would collapse. It might collapse into something else, or perhaps into nothing. Even time might lose coherence. It might no longer flow as a steady sequence of moments. It could break down into fragments that have no order. This is not entirely detached from science. String theory, for example, imagines that the universe may have more dimensions than the one we observe. These dimensions are hidden away at a tiny scale. If these dimensions can be unstable, they could also change or disappear. In another idea, known as quantum gravity, space-time itself is not continuous. It is made up of tiny discrete pieces like pixels on a screen. If those fundamental units of space-time break down or reorganize, the fabric could unravel. The larger fabric they create could also unravel. It is also possible that the laws we take as permanent are only temporary. They may be emergent, arising out of a deeper condition, and if those conditions change, the laws could vanish. This means that dimensional decay would not just be the loss of space, it would be the loss of law, the collapse of the rules that allow the universe to be coherent. If such a decay occurred, there is little that any life could do to resist it. In a heat-death scenario, one might imagine life adapting to a colder and rarer environment, finding a new way to use the last trace of energy. But in a dimensional decay, adaptation would have no meaning. Adaptation assumes a framework of time and space in which action can be taken. If space is gone, there is nowhere to go. If time is gone, there is no sequence in which a choice can exist. This end would not be survivable. It would erase the very idea of survival. Still, one could wonder whether something might remain after such a decay. When a structure breaks down, sometimes its parts create something new. A collapsed star becomes a neutron star. Could the collapse of space and time give rise to another kind of framework, perhaps with different dimensions or rules? In that case, dimensional decay would be a transformation. It would be as if the threads of the universe's fabric were rewoven. They would be rewoven into a new pattern. But whether that would allow life, or anything resembling matter, is uncertain. It could be a cosmos so alien that our words for distance, time, or being would not apply. We might be unable to detect such a decay even if it were beginning. Our measurement of cosmic expansion and energy rely on an assumption, the assumption that space and time are stable. If those dimensions were slowly shifting in a way too subtle to notice, we might misinterpret it. We might interpret the signs as something else, like an unexplained noise or an anomaly in physics. A dimensional decay could be happening beneath our feet. It could be happening beneath the atoms in our body. We would not know until it reached a tipping point. For now, no experiment has confirmed that dimensions can unravel, though some physicists continue to explore whether the universe might face such an end. It stands as a reminder that reality itself may be less solid than we believe. We take for granted features that may not be a permanent fixture of existence. They may be a temporary convenience granted by a universe that one day could take them away. Dark energy and the accelerating universe are stretching time and space. When astronomers first began to measure the expansion of the universe, they had an expectation. They expected to find that gravity was slowing everything down. Galaxies were moving apart, yes, but the pull of their combined mass should have been working against that outward push. Over time, the universe should have been expanding more slowly. It had the possibility of one day halting and reversing. But when a careful observation of a distant supernova was made in the 1990s, the data was surprising. The data revealed that the expansion was not slowing, it was speeding up. This discovery shook the foundation of cosmology. It suggested that some mysterious force was driving galaxies apart faster. It was stretching the very fabric of space itself. That mysterious force was given the name dark energy. Unlike ordinary matter or even dark matter, dark energy is not something that clumps. It does not clump together or gather into a galaxy. Instead, it seems to be spread evenly throughout the cosmos. It is woven into space itself. Its presence acts like a kind of pressure, but instead of pulling things together, it pushes them apart. This push is incredibly weak on a small scale. This is why it doesn't affect the planets in our solar system or the stars in our galaxy. But across billions of light years, its influence becomes overwhelming. The more space there is, the more dark energy there is pushing, the faster the universe stretches. The idea of space itself stretching can be hard to imagine. A common way to picture it is to think of a dot drawn on a balloon. As the balloon inflates, the dots move farther apart. This is not because they are traveling across the surface. It is because the surface itself is expanding. The same is happening to galaxies in our universe. They are not flying through space like a bullet. They are being carried apart as the fabric of space expands. What dark energy does is accelerate that inflation. It is as though someone keeps blowing harder and harder into the balloon. This acceleration has a dramatic consequence for the long-term fate of the cosmos. In a universe without dark energy, gravity might eventually slow expansion. This might be enough for galaxies to remain in closer reach of one another. Instead, dark energy ensures that the gap will only grow. A galaxy that is far away today will eventually move so quickly from our view. Their light will never reach us. They will fade beyond a cosmic horizon. This will leave only the galaxies that are gravitationally bound to us. This means that billions of years from now, a future observer may see little. They may only see the faint glow of their own galaxy. They would see no sign of the wider universe. For them, the evidence of expansion could be erased. Even the very existence of a cosmos beyond their galactic home could be erased. Dark energy makes time itself feel stretched in a strange way. As the universe grows, the rate of its expansion grows too. This changes how we think about the flow of cosmic history. The further into the future we look, the more empty and lonely the universe appears. A region that was once accessible to a telescope or a signal will slip away. It will slip forever out of reach. Space is not only expanding but accelerating toward a future where communication and travel across galaxies will become impossible. Light from a distant galaxy takes billions of years to reach us. But as dark energy stretches space, it also stretches that light. It shifts it toward a longer wavelength. This redshift makes distant galaxies appear dimmer and redder. This happens the further away they are. Eventually, a galaxy becomes so redshifted that its light thins into invisibility. This leaves the night sky darker and emptier with each passing eon. The stars themselves will still shine for a while, but the grand view of a vibrant, expanding cosmos will disappear. What makes dark energy even more puzzling is that its strength does not diminish. It does not diminish as the universe expands. Ordinary matter becomes less dense as space grows. This is because the same number of particles is spread over a larger volume. Radiation thins out even faster as its energy gets stretched by expansion, but dark energy stays the same. No matter how large the universe becomes, it continues to exert the same effect. It exerts the same effect per unit of space. This property suggests it is not a substance in the usual sense. It is something tied to the nature of space itself. Some scientists propose that dark energy could be the energy of the vacuum, a kind of baseline energy that exists even in empty space. Others imagine it as a new type of field that permeates the cosmos. It would change how gravity behaves on a vast scale. But so far, no experiment on Earth has been able to directly measure it. We only see its fingerprint in the way galaxies move. We also see it in the pattern of light left over from the Big Bang. If dark energy continues to act the way it does now, the universe will keep accelerating. But there are more extreme possibilities. If the force of dark energy grows stronger with time, it could tear things apart. It could eventually tear apart galaxies, solar systems, and even atoms. This is a scenario sometimes called the Big Rip. In this vision of the future, everything would be pulled apart. This would happen as space itself stretched infinitely fast. On the other hand, if dark energy weakens or changes its nature, things could change. The universe might settle into a slower pace or even reverse. It could collapse back into a final crunch. For now, the best evidence points to a future of endless acceleration. Galaxies will drift apart until each one becomes an island of stars. They will be surrounded by darkness. Beyond their edge, the universe will be unreachable. It will be locked away by the relentless expansion of space. In this way, dark energy not only shapes the present, it dictates the distant destiny of all that exists. It stretches not only space, but also the meaning of time. It creates a cosmos that is both vast and fleeting. It is filled with countless galaxies, but destined to hide them from view. The cold, empty universe, life beyond the heat death. Could anything, in any form, still exist in a cold, empty universe? If life is known for its persistence, perhaps even a quiet form of it could stretch on. It could stretch beyond what we think of as an ending. To imagine such a future, it is helpful to think of what life requires. Every living thing that we know depends on a flow of energy. On Earth, plants capture energy from the sun. Animals feed on that energy indirectly. Even a bacterium in a deep ocean finds chemical energy to sustain itself. Energy is the spark that allows order to resist the natural pull of disorder. But in the far future, when the universe reaches its heat, that spark will be gone. It will be almost impossible to find. Energy will be spread out so evenly. There will be no natural flow from one place to another. Without a gradient, without a difference in temperature, there is no way to draw power. And yet some have wondered whether the last flicker of energy could be stretched. It could be drawn out in a way that allows some form of activity to continue. Physicists sometimes speculate about an extremely slow process, a civilization or a being that operates on a time scale so long. What seems like nothing to us could be meaningful to them. Imagine a mind that only thinks once every trillion years. It would wait patiently for a tiny shift in the background radiation. Or it might wait for the rare collision of a decayed particle. To us, such a life would appear frozen like a stone. But from its perspective, there might still be thought, memory, and even an awareness. Others have suggested that perhaps a structure could form from space-time itself. It would not form from energy as we know it, but from the very fabric of space-time. Quantum mechanics hints that empty space is not truly empty. A tiny fluctuation occurs, constantly giving rise to virtual particles. They flicker in and out of existence. In today's universe, these fluctuations are so small that they barely matter. But in the deep future, when all other sources of energy are gone, they may be all that's left. They may be the only thing left to work with. Could an advanced form of life, if it somehow survived, learn to draw on these fluctuations? Could they find a way to spark an activity in a sea of stillness? Some scientists have considered that information itself could serve as a kind of life. It could serve as life in the far future. If matter is gone and energy is useless, perhaps patterns of information could be preserved. Information stored in a quantum field could be preserved in some form. Life, after all, can be described as information organized in a way that resists decay. The cells in your body are a pattern of molecules carrying the code of DNA. Could there be a way for a pattern of information to continue? Could it continue even when the physical carrier of life is no longer available? This idea moves into a very speculative territory, but it reflects the drive to imagine survival in the face of absolute stillness. The heat, death of the universe is not expected for a very long time, at least 10 to the power of 100 years. This number is so large it defies true comprehension. By then, not only will stars and galaxies be gone, but even protons may have decayed. This would leave nothing but radiation and the occasional particle drifting in darkness. If life, or something like it, were to exist in such a time, it would be unrecognizable. It might exist as a rare, scattered pulse of activity in an otherwise silent ocean. A philosopher sometimes describes this imagined existence as a ghost life, one that clings on not in the way we understand. It clings on in a way that stretches the very definition of what life means. Would such a being, if it could think, even consider themselves alive? Or would they simply be the last echo of a universe that once held stars, a universe that once held a galaxy and a world filled with wonder? Perhaps the laws of physics as we know them do not allow for persistence. Not once energy has reached a complete equilibrium. In that case, the story of life would be a brief chapter in the history of the cosmos. A flame that flared brightly for a time and then went out, leaving only darkness. To some, this idea is troubling. To others, it is poetic, a reminder of the preciousness of the moment we have now. Still, the imagination does not stop there. Some theorists wonder whether a new universe could be born. Could it be born even out of the ashes of a heat death? If a quantum fluctuation is real, perhaps one of them could grow into something larger, a bubble of energy that expands, igniting a new Big Bang. In that sense, the universe may never truly die. Instead, it may give birth to countless new universes, each with its own story. If that is true, then perhaps life, or something resembling it, will always find new ground. It will always find new ground to take root in. Our science gives us an outline, a probability, and a mathematical model. But it cannot yet tell us exactly what will happen. What is clear is that life as we know it cannot continue in such a universe. But whether some new, almost unrecognizable form of existence might arise is a question. It is a question that lingers. It is a question that reflects not only the limits of physics, it also reflects the endless reach of human imagination. Perhaps in the shadow of nothingness, something unexpected waits. Something that could turn the end into another kind of beginning. The decay of space will the fabric of the universe fade away. Space is seen as the quiet backdrop against which everything else unfolds. A star burns, a galaxy drifts, a black hole swallows, and a planet circles. All of this happens within the invisible fabric we call space-time. It feels permanent, like a canvas that cannot tear, bend, or fade away. Yet some physicists have asked the question, what if this very canvas is not eternal? What if the fabric of space itself can decay? What if it slowly erodes until nothing remains, not even an emptiness? This idea sounds strange, almost unsettling, because space already seems like nothing. But nothing in physics is not the absence of existence. It has rules, a structure, and an energy built into it. Space expands. It bends under the pull of matter, and it allows time to tick forward. It may seem passive, but it is deeply active in shaping everything we know. If space-time itself has a kind of built-in fragility, then the long future is different. The long future of the cosmos may not just be cold or dark. It may be unstable at its very foundation. One way scientists explore this possibility is through the idea of a vacuum decay. In physics, the word vacuum means the lowest possible energy state of a space. But what if the vacuum we live in is not truly the lowest state? What if it is only a temporary one? Imagine a ball resting in a shallow valley. It looks stable, it doesn't roll away, and it could stay there for an age. But beyond the hill, there might be a deeper valley, a more stable resting point. If the ball were to roll over into that deeper valley, the state would change. The state of the whole system would change. In the same way, our universe could be resting in what is called a false vacuum. It may not be the deepest possible version of reality. If this is true, then space as we know it could one day decay into a new form. A bubble of a true vacuum might suddenly appear in some distant region. It could be triggered by a quantum fluctuation. This bubble would expand at nearly the speed of light. It would rewrite the very rules of physics inside it. The forces that hold atoms together, the structure of time, and even the existence of matter. All of these could vanish or transform beyond recognition. For anything caught in its path, there would be no warning and no escape. To an outside observer, this would be the ultimate erasure. It would be as if the universe itself had rewritten its code. This is a deeply speculative idea, but it flows naturally from the equations of quantum field theory. This is the same mathematics that describes particles, energy, and the early universe. Some researchers point to the properties of the Higgs boson. This particle was discovered in 2012. Its properties may be a possible clue. The measured mass of the Higgs seems to suggest our vacuum might be metastable. It would be balanced precariously between stability and collapse. If so, then space-time itself carries within it the possibility of an eventual decay. Another scenario considers whether the expansion of the universe itself weakens space-time. As dark energy drives galaxies apart, space stretches faster and faster. Could this stretching tear the very fabric, leaving behind nothingness? This would be a big rip scenario. In this picture, the acceleration does not stop. It grows so extreme that it eventually overwhelms all forces. Galaxies are torn away from each other, stars are ripped apart, planets are shredded, and finally atoms themselves are pulled into nothing. What remains would not be a new structure of space, but the collapse of structure. In the Big Rip, space-time does not just fade, it unravels. Even if no dramatic ripping or bubble decay occurs, there is a quieter prospect. This prospect is equally haunting. It is the gradual thinning of space-time. Just as heat spreads evenly in the vision of a heat death, space-time could thin. One could imagine the fabric of space becoming less dynamic and less structured. It could become more ghost-like as time rolls on. The stretching could dilute not only matter and energy, it could also dilute the capacity of space-time to hold anything at all. In the far future, beyond trillions upon trillions of years, we may face a cosmos where space exists only in name, with no property left to sustain events. The most extreme version of this asks whether time itself would come to an end. If space-time is not permanent, then the ticking of a moment may not be either. Our universe could reach a final pause where time no longer advances. This could happen because the medium that carries it, the fabric of space, has ceased. It would have ceased to exist. To us locked inside the current form of reality, this is almost impossible to picture. What does it mean for a time not to pass? How can anything end if there is no future? It is like asking what lies beyond the edge of existence itself. And yet, even if these scenarios are terrifying, they may also be natural. After all, nothing in the cosmos seems eternal. A star burns out, a galaxy fades, a black hole evaporates. Why should space itself be exempt from change? We are used to thinking of it as eternal and invincible. But perhaps it is just another actor in the cosmic drama. Perhaps it is destined to have an ending. If that is true, then the universe is not a stage that holds the play. It is a part of the play itself, rising and falling with everything else. Could life ever survive such a change? Could an intelligence somehow anticipate and adapt to a rewritten universe? Or would all memory of our existence be wiped clean? Is the decay sudden, like the burst of a bubble, or slow like a fading echo? Each version paints a different picture of the far future, but all share one thing in common: the recognition that the universe is not guaranteed. It is not guaranteed to last in the form we know it. If a vacuum decay is real, it could begin anywhere at any time without warning. It could be happening right now, billions of light years away. A bubble could be expanding invisibly through the cosmos. Or it may never happen, and our vacuum could endure forever. We simply do not know. The fate of space itself may rest on a property we have barely begun to measure. For now, all we can do is imagine. We gaze at the stars and wonder about galaxies, about black holes, about heat death. But behind all of these lies, the deeper question is the very fabric holding it all together stable. If it is not, then the ultimate ending of the universe is not just a cold emptiness. It is a transformation into something unprecedented. Or perhaps it is the end of reality itself. The decay of space is not simply another step in a cosmic evolution. It is the possibility that there may come a time when even the idea of a universe no longer makes sense. Time's end, the final moment of the universe's clock. What happens to time when everything else has ended? Time is usually thought of as the stage on which all events play out. But if the stage itself collapses, what does that mean for the story? To imagine the final moment of the universe is to think about more than death. It is not only to think about the death of matter and energy, it is also about whether time can come to a halt. In our everyday life, time is so constant and reliable, it feels separate from the things inside it. We wake up, the clock ticks forward, and we assume something. We assume that no matter what happens, time will always be there keeping count. Yet in physics, time is not independent. It is bound up with space woven into the very geometry of the universe. Together, they form space-time. And space-time is not unchanging. It bends, stretches, and evolves. That means time itself is a part of the story of the universe. It has a beginning tied to the Big Bang. It has a possible end tied to the ultimate fate of everything. As the universe expands, time stretches along with space. The ticking of the cosmic clock is not the same everywhere, nor has it been the same throughout history. In the very early universe, time advanced through a storm of energy. It advanced through particles and rapid inflation. Later, it slowed down into the calmer rhythm of galaxies and stars. Today, it ticks in a way shaped by dark energy as expansion accelerates. Looking into the far future when galaxies are pushed farther apart, one wonders, does time simply continue endlessly marking moments in an empty void, or does it too run out? One way to think about this is through the heat death scenario. In this vision of the far future, energy becomes evenly spread out. No more useful work can be done. If nothing ever changes, if no new event occurs, then what meaning does time have? Time is at its heart a measure of change. Without change, does time still exist, or is it indistinguishable from non-existence? Some scientists argue that in this state, time would lose its practical meaning. This is true even if mathematically it continues. The universe would not end with a bang, but with a silent fading into timelessness. But there are deeper possibilities. In physics, time is not only a concept of change, it is also a dimension tied to the structure of space-time. If space itself stretches without a limit driven by dark energy, then time must also stretch. In this case, the clock would keep ticking forever, but it would tick at a pace so stretched that the difference between moments could grow. In the farthest future, the difference could grow beyond comprehension. In an empty and accelerating universe, time could dilute. It could dilute in the same way matter and energy do. It would still be present but stretch so thin that its reality becomes ghostly. On the other hand, if the universe does not expand forever, time might not stretch. If it instead meets some catastrophic end. If a big rip tears apart galaxies, stars, atoms, and even space-time, time would shred. The fabric of time would shred. The clock of the universe would not only stop but be destroyed. It would leave no framework in which a before or an after could exist. In such a case, the final moment of time would arrive as an absolute boundary. Beyond it, there would be nothing. It would not even be the absence we usually imagine when thinking of a void. Another possibility lies in the decay of the vacuum. If this field is not perfectly stable, it could one day collapse. This would create a bubble of new physics. Within it, the rules of reality might be rewritten, including the structure of time. If such an event occurs, it would erase the timeline of our universe. It would cut it short abruptly. The last tick of the clock would be swallowed, and time as we know it would be no more. Even more speculative is the idea that time is not fundamental at all. Some physicists suggest that time might emerge from a deeper physical law. In this view, time is not a basic ingredient of the universe. It is something that arises from the way matter and energy interact. If so, when those interactions fade, when the universe drifts into a state of maximum entropy, at that point, time might dissolve. The universe would not only be empty of stars and galaxies, it would also be empty of the very flow that carried them through existence. Our sense of time is built from memory and expectation. We remember what has happened, and we imagine what will happen. If the universe reaches a point where no event occurs, the difference disappears. Where no new moment can be distinguished, the difference between now and then disappears. For a conscious observer, this would mean slipping into an eternal present. There would be no change to mark the passing of a moment. It is not so much the end of time as the loss of its meaning. Some thinkers speculate about what could lie beyond time's end. This is difficult to imagine because every thought we have is tied to time. Our thoughts are tied to the notion of time moving forward. To picture an existence without time is like trying to see without space. It feels impossible. Yet if time is a part of the universe's structure, then if that structure dissolves, so too might time. In that case, there is no beyond. The story simply ends not because something new follows. It ends because there is no framework left for anything to happen, and yet there remains the possibility of a cycle. Some cosmological theories suggest that time might not end permanently. It might instead reset. In a bouncing model of the universe, the end of one cosmic timeline could seed another. It could seed the beginning of another. Time could collapse and then restart with a new arrow pointing forward. If this is the case, then what looks like the end of time might be temporary. It might only be the end of one version of it with another waiting to begin. How time ends remains a great mystery in cosmology. What we do know is that time is not guaranteed. It is fragile, bound to the physics of space and energy. It is woven into the fate of the cosmos itself. To think about the last tick of the universe's clock is to stretch the imagination. It stretches the imagination to its limit. It is to face a possibility stranger than any emptiness, the erasure of time itself. This would leave not a void but an absence so complete that no word, no thought, no measure could capture it. The potential for a quantum resurrection. Can we reignite the universe? Could a quantum chance breathe life back into a cosmos that has grown cold, a cosmos that has grown still? If the right kind of fluctuation occurred, it might gather enough energy. It could trigger a new burst of expansion like a miniature version of the Big Bang. In such a case, a patch of space could suddenly inflate, creating a new universe. Our universe would not have truly ended. It would have given birth to another through the chance working of quantum mechanics. This idea connects to what is sometimes called an eternal inflation. In this view, our universe itself may be just one bubble among many. The Big Bang might not have been the one true beginning. It might have been only a local event, a spark inside a much larger reality. If so, then the end of our universe might not be a final wall. It might only be a doorway to the possibility of a new universe forming. A quantum fluctuation could ensure that creation never fully stops. This is true even if one universe fades into nothingness. But there is another stranger layer to this thought. It deals not with an entire universe, but with a smaller, localized event. Some physicists have speculated about what is sometimes called a Boltzmann brain, a self-aware structure that might randomly appear from quantum chaos. The idea is that given enough time in a universe approaching heat death, something could happen. A chance fluctuation might briefly form a complex structure, even a pattern of thought. This would resemble a living mind. These brains would not last long. They would dissolve almost as quickly as they appeared. But they represent a shocking possibility. In the final silence of the universe, an isolated spark of awareness might still flicker. It could flicker into existence, unconnected to a star or a planet or a galaxy. If chance alone could create such complexity, then a resurrection might be possible. The resurrection of an entire universe might also be possible. It would not be a resurrection in the sense of restoring what was lost. Instead, it would be something new, something born out of a randomness. Just as the Big Bang may have been a sudden and unexplained release of energy, a future fluctuation might create another moment of expansion, another reset of time, another chance for creation. The difficulty is scale. At the quantum level, a fluctuation is common but small. They happen all the time in the vacuum of space. What would be required is an immense fluctuation, one capable of sparking an inflation and building a whole new universe. The odds of such an event are unimaginably low, but the universe has one advantage. In a cosmos that stretches on not for billions or trillions of years, but for a number beyond human imagination, even the most unlikely event might eventually occur. A fluctuation that would seem impossible on a human timescale could become inevitable. It could become inevitable when the clock runs for an eternity. If such a new universe did emerge, what would it look like? Would it carry the memory of the old, or would it be entirely fresh? Most theories suggest the latter. The birth of a new universe through a quantum fluctuation would erase details. It would erase the details of the one before. Its physical constants might be different. Its dimensions might not match ours. It might be unrecognizable, governed by strange rules. In that sense, it would not be our universe reborn. It would be a stranger, a new reality unfolding from the ashes of the old. There is also the question of whether such a rebirth could be observed at all. From within our universe, there may be no way to detect it. A fluctuation that creates a new bubble universe might cut itself off. It might cut itself off completely from our own. To us, the universe would still appear to end in a heat death. There would be no visible resurrection. The new reality would blossom in isolation, hidden from any eye that might have looked. If a universe can be born from a fluctuation, then perhaps reality is a chain. Reality as a whole is an endless chain of birth and death. Each universe may run its course cool and fade, only for another to spark into being. It could spark into being somewhere in the quantum sea. This cycle could go on forever without a need for a beginning or an end. Our universe would then be just one link in an infinite story. One moment in a chain that stretches beyond time itself. This picture is comforting because it suggests that creation never truly stops. Even after our universe dies, reality itself will go on. But it is also unsettling because it suggests that our universe is not special. It may be only one of countless experiments played out by chance. It may have no guiding hand or an ultimate purpose. The resurrection offered by quantum mechanics is not the return of what was lost. It is the endless possibility of something new. It is born not from a design but from a randomness. Alternative endings to the universe. When people first began to think about the universe's end, one idea seemed natural. The idea of a big crunch seemed natural. If the universe started with a bang, maybe it would end with a collapse. The thought was simple. Gravity pulls everything inward. If there was enough matter, enough energy, then the expansion of the universe would stop. It would slow stop and reverse. Galaxies would drift closer, stars would gather again, and everything would collapse. It would collapse into one final, unimaginable point of density and heat. This vision of the cosmos carried a strange symmetry. It was a neat circle where the end mirrored the beginning. Yet as science advanced, and new observations were made, the Big Crunch became less certain. The universe, it seemed, might not close in on itself after all. Instead, it could follow another path. With dark energy at work, the universe does not seem to be heading toward a collapse. Instead, it is racing outward with an expansion accelerating faster and faster. If this continues, the universe might never come back together. Instead, it may face an ending stranger than the neat symmetry of a crunch. One of these possible endings is called the Big Freeze. In this vision, the universe expands forever over an unimaginable timescale. Everything fades. What's left is a universe of thin radiation, scattered particles, and darkness. It does not collapse, but it does wither away into a silence. The Big Freeze is not explosive or violent, but it is absolute. It represents the slow death of everything stretched over trillions of years. Another idea is the Big Rip, which would be a violent, all-consuming unraveling. It would unravel the fabric of reality. Instead of fading into a quiet darkness, the universe would end in chaos. It would be pulled apart by its own runaway expansion. But the possibilities do not stop there. Some scientists imagine a stranger cycle where the universe might experience a rebirth. In one version of this idea, dark energy itself could change over time. If it were to weaken, expansion might one day slow and reverse after all. This would lead to a collapse, but not into a final dead end. Instead, that collapse could ignite another Big Bang. It could give rise to a new universe. This repeating pattern is sometimes called the Big Bounce. In it, a universe may die and be born again endlessly. There would be no first beginning and no final end. Other theories imagine our universe might give birth to a new one instead of ending. The false vacuum idea has already been discussed, but there are also ideas that focus on the very structure of space-time. If space-time is not smooth but instead has a hidden layer or dimension, things could change. Then the universe might not simply expand forever. Instead, it could one day tunnel into another state. In quantum physics, even a thing that seems impossible can sometimes happen. It can happen through a rare fluctuation. The entire universe could undergo such a change. It could fall into a new configuration of reality. To the beings inside, it would appear as the sudden end of everything. But on a larger scale, it could mark the beginning of something else entirely. Each of these visions carries its own kind of weight. The Big Crunch gave people a simple story of a return. It was a comforting balance between a beginning and an end. But the alternatives are harder to grasp. The Big Freeze speaks of an endless emptiness, a future where not even a memory can survive. The Big Rip paints a picture of destruction so complete, even the smallest building block is torn away. The Big Bounce and related ideas offer an endless cycle where death is never final. And quantum models hint at a transformation beyond our ability to imagine. The very rules of reality could shift in an instant. The search for which of these paths is most likely is ongoing. Scientists look at the motion of galaxies, the behavior of dark energy, and space-time. They look at the deepest structure of space-time itself. But the universe guards its secrets well. The timescales are too vast, the energies too extreme for us to test directly. What we are left with is a glimpse, a pattern of light, a faint signal, a tiny shift in the expansion rate. From these fragments we try to piece together a story about the ultimate fate of everything. A civilization in the far future, will they adapt or perish? For any civilization alive in the deep future, survival would be a challenge. They would confront conditions beyond anything we can picture from our short-lived age. What would an intelligent being do in such a place? Would they find a way to adapt, or would they fade along with the dying cosmos? The first challenge would be energy. All life as we know it, and all technology, depends on a source of power. A civilization grows and thrives because they can use the energy of their environment. This could be fire, the burning of fossil fuels, the flow of a river, or fusion in a star. But as the stars age and exhaust their fuel, the great furnaces will shut down. The night sky of a far future world would not be filled with glittering light. Instead, it would be empty, with only a few faint embers, a few red dwarfs or cooling white dwarfs glowing weakly in the dark. A civilization living in that era would have to turn elsewhere for power. They might tap into a black hole. For trillions of years, black holes will remain some of the most energetic objects. Matter falling into them releases a vast amount of energy, and even their slow evaporation through Hawking radiation could, in theory, be harnessed. An advanced being could build a structure to capture this energy. They could feed matter into the black hole to prolong the supply. Instead of sunlight, their world might be lit by an artificial system. It would be powered by the slow death of a black hole. The thought is strange, but not impossible. A civilization growing like a parasite on the last flame of creation, clinging to the few places where energy can still be extracted. Another possibility could involve tapping into the decay of matter itself. If protons eventually break apart, as some theories suggest that decay would release energy, a civilization could attempt to collect and channel the faint trickle of power. It would be a trickle from matter falling apart at the smallest scale. It would not be much, but it could be enough for some beings. For a being with a time horizon stretching across billions of trillions of years, even the smallest energy could be carefully preserved and stretched. Their life would become a constant struggle against a dwindling fuel, an existence where patience and efficiency matter more than expansion or growth. But perhaps an adaptation would not only be physical. In a universe where physical resources are scarce, a civilization might turn inward. Instead of building a vast empire among the stars, they could collapse into themselves. They could retreat into a digital or a simulated world. If they had the technology, they could upload a consciousness into a machine. They could exist as a stream of information within a computer that runs on as little energy as possible. An entire society could live in a world of thought. Their civilization could continue in a form unimaginable to us. For such a being, the outside cosmos might become irrelevant. It would be a frozen void they no longer need to engage with. Their survival would not be about mastering the universe. It would be about mastering themselves. Of course, this assumes that a civilization reaches such a level of technology. Many may not. If history shows anything, it is that civilizations rise and fall. They are often undone by their own choices, long before the environment forces them out. For a being in the deep future, the question may not just be how to survive, not just how to survive a dying universe, but whether they can endure the challenge of their own nature. The longer a civilization exists, the more chance there is for a mistake, a war, a collapse, or a choice that locks them into a decline. It could be that very few ever survive long enough to face the final cooling, and yet some might. For those that do, the universe will not be kind. The vast distances between surviving islands of matter will grow even greater. This will happen as cosmic expansion continues. Communication across the universe will become impossible. Civilizations will find themselves in a deep isolation. If more than one survives, they may never know of each other's existence. Each will become the last light of its own region of space. Each will be imprisoned in a solitude. A civilization may adapt not by fighting to survive forever, but by choosing to end. Perhaps there comes a point when a people accepts the futility of holding on against the slow death of the cosmos. They could decide to end their existence on their own terms. They could fade away while their world still holds some energy and light. It would be a kind of surrender to the universe's fate, a recognition that no struggle can outlast entropy. Others might instead resist fighting endlessly to stretch their survival. They would stretch it into the coldest reaches of time. They would refuse to give in even as energy dwindles to almost nothing. There is also the chance that a civilization would try to rewrite the rules. Maybe they would attempt to create a new universe through a quantum fluctuation. Or they might tap into a dimension beyond our own. If any being in the far future discovers such a possibility, they might try to escape. They might attempt to escape into a fresh cosmos, carrying their knowledge with them. In that sense, adaptation would not mean living in the dying universe. It would mean leaving it entirely, planting a seed of civilization in a newborn reality. For us, 1,000 years feels vast. For the universe, 1,000,000,000,000 years is a blink. A civilization, if it survives that long, would measure their life in ages, ages beyond comprehension. To adapt in such an environment would mean planning for a span of time greater than the age of our universe today. The patience, wisdom, and resilience required would be unlike anything we can imagine. A being of that future would think and act at a pace completely alien to us. They would be shaped by a universe that moves slowly towards a silence. Still, one wonders whether meaning itself could survive. A civilization may adapt physically, finding a way to keep energy flowing. They may keep life continuing. But in a universe growing steadily colder and darker, what purpose would drive them? Our own civilization is bound to stories, hopes, and dreams. These are tied to a growth and an exploration. In a cosmos where nothing new is possible, where the stars have all burned out, would hope fade? Or would a civilization find a new meaning in endurance? A new meaning in the simple act of persisting against the night? Perhaps survival would not mean existing forever, but existing long enough to create something lasting. A civilization might adapt for as long as they can. In the process, they may leave behind a trace, a structure, or a signal. Or they may leave an entirely new universe that outlives them. Their legacy could be written into the fabric of reality. This is true even if they themselves eventually fade. In that way, the struggle against the dying universe would be about leaving an echo that says they were once here. And on that bittersweet note, today's journey comes to an end.